Most people think of a black hole as the final destination in nature, a place where stars die, a place where matter disappears, a region so completely cut off from the rest of the universe that nothing, not even light itself, can ever return. It seems like the closest thing the cosmos has to an ending. For decades, that picture has served us remarkably well. It explains why black holes appear as perfect silhouettes against glowing gas. It explains why stars orbit invisible objects containing millions or even billions of times the mass of our sun. It explains the ripples in space itself that wash across Earth whenever distant black holes collide. Yet beneath this familiar understanding lies a quiet uncertainty. Modern physics describes, with extraordinary precision, what happens outside a black hole. We can calculate the paths of stars circling its edge. We can predict how light bends around its immense gravity. We can even measure the waves produced when two black holes merge over 1 billion light-years away. But the moment we ask a seemingly simple question, our confidence begins to fade. What actually happens inside? The answer is unexpectedly elusive, not because scientists have ignored the question, but because nature seems to hide the answer behind a boundary that cannot be crossed from our perspective. The event horizon acts like a one-way curtain. Information can fall inward. Nothing that carries news of what lies beyond can return. It is one of the strangest situations in all of science. Humanity has built telescopes that peer nearly to the beginning of time. Spacecraft have crossed the solar system. Detectors buried beneath mountains can observe particles that pass through entire planets. Yet the interior of a black hole remains forever hidden. This raises an unsettling possibility. Whenever science encounters a place where observation ends, imagination is tempted to take over. History offers countless examples. Ancient civilizations filled unknown oceans with monsters. Early astronomers imagined perfect celestial spheres because they could not see beyond them. Every generation has discovered that reality is usually stranger, but also more subtle, than its first assumptions. Black holes occupy exactly this kind of frontier. The difference is that today's speculation is guided not by myth, but by mathematics. Some of the world's most respected physicists have noticed something peculiar. When the equations describing gravity are followed all the way toward the center of a black hole, they arrive at a destination that seems impossible. Density becomes infinite. Space shrinks to zero. The known laws of physics cease to produce meaningful answers. Whenever infinity appears in physics, it often signals that the theory itself has reached its limit. This has happened before. Classical physics predicted that atoms should collapse, yet they do not. Quantum mechanics revealed an entirely different picture hidden beneath the old one. Classical gravity described Mercury's orbit almost perfectly, until tiny discrepancies led Einstein to develop general relativity. Again and again, nature has shown that apparent impossibilities often point toward deeper truths. Could the singularity inside a black hole be another such sign? If the mathematics is incomplete, then perhaps the destination we imagine does not truly exist. And if there is no infinite point where everything simply ends, then what replaces it? That question has inspired one of the most fascinating ideas in modern cosmology. Perhaps the immense pressure inside a black hole never compresses matter into an impossible singularity. Instead, under conditions where quantum effects become overwhelmingly important, the collapse could stop. Not gently, not dramatically, simply because nature itself refuses to permit infinities. If so, the inward journey might transform into something entirely different. Instead of ending, space itself could begin expanding again. Not into our universe, into another. This idea sounds almost like philosophy at first hearing. Yet it arises from genuine attempts to reconcile two of humanity's greatest scientific achievements. General relativity describes gravity across galaxies with astonishing accuracy. Quantum mechanics governs the invisible world of atoms and elementary particles with equal precision, separately. Each theory is among the most successful scientific frameworks ever created. Together, at the heart of a black hole, they refuse to cooperate. That disagreement is more than an academic puzzle. It suggests that somewhere beyond our current understanding lies a deeper description of reality, one capable of explaining both gravity and quantum physics simultaneously. Some researchers believe that when such a theory is finally discovered, black holes may look profoundly different from the way we picture them today. Instead of cosmic prisons, they could become cosmic bridges. Instead of endings, beginnings. Instead of destroying information forever, they might reshape it into entirely new forms of existence. None of these ideas are established facts. It is important to separate what astronomers have observed from what theoretical physicists are exploring. We have overwhelming evidence that black holes exist. We know stars collapse into them. We have photographed the shadows cast by supermassive black holes. We have measured gravitational waves from their collisions. These belong to observation. The suggestion that black holes create universes belongs to a different category. It is a hypothesis, a serious one, grounded in mathematics and developed by respected scientists, but still awaiting evidence that could distinguish it from competing explanations. That distinction matters. Science advances not by certainty alone, but by carefully exploring uncertainty without pretending it has already been resolved. In many ways, the mystery surrounding black holes reflects the broader story of astronomy itself. Every time humanity believed the cosmos had become familiar, another horizon appeared. Earth was not the center. The sun was not unique. Our galaxy was not alone. The observable universe may not even represent all that exists. Perhaps black holes are simply the next horizon waiting to reshape our perspective. If they truly conceal new universes, then every galaxy scattered across the night sky may contain countless unseen beginnings hidden within its darkest regions. And if our own universe emerged through a similar process long ago, then the oldest question in cosmology quietly changes. Instead of asking what existed before the universe, we may someday ask something even more profound. Inside what kind of cosmos was our own universe first born? The first step toward understanding whether black holes might create universes is to set aside the mystery for a moment and return to what astronomy already knows with remarkable confidence. Long before black holes became symbols of cosmic mystery, they were simply a consequence of gravity. Gravity is the quiet architect of the universe. It gathers tiny grains of dust into planets. It binds planets to stars and stars into galaxies. It stretches invisible bridges across millions of light years, holding together vast clusters of galaxies whose combined mass is almost beyond comprehension. For most of our daily lives, gravity feels gentle. A dropped leaf drifts toward the ground. Ocean tides rise and fall under the influence of the moon. Even the sun's immense gravity allows Earth to travel in a graceful orbit rather than pulling it inward. But gravity has another side. When enough mass is squeezed into a small enough volume, gravity no longer behaves as the calm force we experience on Earth. It becomes overwhelming, capable of bending space and time themselves. This is where the story of black holes truly begins. Most stars spend the majority of their lives balancing two opposing forces. Gravity constantly tries to pull the star inward. At the same time, nuclear fusion deep within the core releases enormous amounts of energy, pushing outward. For millions, or even billions of years, these two forces exist in delicate equilibrium. A star shines because of this balance. Every second, our own sun converts hundreds of millions of tons of hydrogen into helium. The energy released from this fusion slowly works its way outward before escaping into space as sunlight. Without that outward pressure, gravity would immediately begin compressing the sun. Eventually, however, every star exhausts its nuclear fuel. What happens next depends almost entirely on mass. Stars similar to the sun gently shed their outer layers, leaving behind dense white dwarfs that slowly cool over trillions of years. Much larger stars face a more dramatic fate. Once fusion can no longer support their immense weight, gravity wins almost instantly. The core collapses in a matter of seconds. Electrons are forced into protons, producing neutrons and a flood of neutrinos. The outer layers rebound in a spectacular supernova explosion, briefly outshining entire galaxies. Sometimes the remaining core becomes a neutron star. A single teaspoon of neutron star material would weigh billions of tons on Earth. Yet even neutron stars have limits. If the collapsing core contains enough mass, not even the pressure between neutrons can resist gravity forever. Collapse continues. According to general relativity, nothing stops it. The object becomes so compact that its escape velocity exceeds the speed of light. That simple statement carries extraordinary consequences. Escape velocity is the speed required to leave an object's gravitational pull. On Earth it is about 11 kilometers per second. On the Moon it is only about 2.4 kilometers per second. For the Sun it exceeds 600 kilometers per second. As gravity grows stronger, escape velocity increases. Eventually it reaches 300,000 kilometers per second. the speed of light itself. Since nothing with mass can travel faster than light, a boundary naturally forms. This boundary is known as the event horizon. The event horizon is often misunderstood as a physical surface. It is not. A spacecraft crossing it would not strike a wall or encounter an invisible shell. Instead, the event horizon is better understood as a point of no return. Outside it, moving away from the black hole remains possible. Inside it, every possible future path leads deeper inward. Even light, which always travels at its maximum possible speed, cannot escape. This simple concept explains why black holes appear perfectly dark. They emit no light of their own because any light produced inside the horizon remains trapped forever. Ironically, black holes often become some of the brightest objects in the universe. This apparent contradiction arises because matter rarely falls directly into them. Gas and dust usually spiral inward, forming an accretion disk that becomes unimaginably hot. Friction between particles raises temperatures to millions of degrees. The glowing disk radiates powerful X-rays and visible light before the material finally disappears across the horizon. In some galaxies, supermassive black holes launch enormous jets of particles traveling at nearly the speed of light. These jets can extend for hundreds of thousands of light years, influencing the formation of entire galaxies. Far from being passive consumers of matter, black holes actively shape the cosmos around them. Over the past century, evidence for their existence has grown steadily stronger. Astronomers first noticed stars orbiting invisible companions far heavier than any normal star could be. Later, X-ray telescopes revealed compact objects consuming gas from neighbouring stars. The motion of stars near the centre of the Milky Way pointed unmistakably toward an unseen object containing about 4 million times the mass of our Sun. No known cluster of ordinary matter could remain stable while producing such gravitational effects. Only a supermassive black hole fit the observations. Then came an extraordinary achievement. In 2019, the Event Horizon Telescope combined radio observatories across Earth into a planet-sized virtual telescope. Its first image did not show the black hole itself. That remains impossible. Instead, it revealed the glowing ring of hot gas surrounding the shadow cast by the event horizon of the supermassive black hole at the centre of the galaxy M87. For the first time, humanity could see the silhouette of one of nature's strangest objects. A few years later, the same international collaboration produced an image of the black hole at the centre of our own galaxy, although blurred by turbulent gas between the stars. It matched the predictions of Einstein's theory with remarkable precision. At nearly the same time, another revolutionary field of astronomy emerged. Gravitational wave observatories began detecting tiny ripples in space and time produced when black holes collided. These signals travelled across the cosmos for billions of years before gently stretching and compressing Earth by distances smaller than an atomic nucleus. The patterns matched theoretical predictions almost perfectly. Today, thousands of independent observations support the conclusion that black holes are real. Their masses can be measured. Their spins can be estimated. Their influence on nearby stars, gas, and even entire galaxies can be observed. In that sense, black holes are no longer speculative objects. They are established members of the cosmic landscape. Yet something remarkable remains true. Every observation we possess concerns what happens outside the event horizon. The stars we track orbit safely beyond it. The glowing gas shines before crossing it. The gravitational waves are produced by the motion of black holes around one another, not by events deep within them. Even the famous images reveal only the boundary where light narrowly escapes. The interior itself remains hidden. It is rather like standing beside a vast ocean at night. The waves, the tides, and the reflections on the surface tell us much about the water beneath. But no matter how carefully we observe the surface alone, we cannot directly see the deepest currents below. That hidden interior is where our journey now turns. For although black holes themselves are no longer mysterious in the way they once were, the greatest question has scarcely been touched. What becomes of space and time after something passes forever beyond the event horizon? The answer lies where our most successful theories begin to disagree. For centuries, the history of physics has been a story of increasing confidence. Each generation inherited mysteries that seemed impossible to solve, only to discover that nature, while often surprising, remained remarkably consistent. Newton explained the motions of falling apples and orbiting planets with the same elegant laws. Maxwell united electricity and magnetism into a single theory. Einstein showed that gravity was not a force acting across empty space, but the curvature of space and time themselves. Each breakthrough expanded humanity's understanding without overturning everything that came before. Older theories remained useful within the limits where they had always worked. General relativity became one of the greatest successes in this tradition. Its predictions have passed every experimental test thrown at them for more than a century. It explains why clocks run slightly slower near massive objects. It predicts the bending of starlight during solar eclipses. It accurately describes the expansion of the universe and the motion of galaxies. Even the existence of gravitational waves, once considered almost impossible to detect, has now been confirmed many times. If the universe were written in a single language, general relativity would seem to describe its grammar with astonishing elegance. Yet every language has words it cannot quite express. For general relativity, that word is the singularity. According to Einstein's equations, if enough matter collapses under its own gravity, there comes a point where the curvature of space and time increases without limit. Distances shrink towards zero. Density rises without bound. The mathematical quantities describing gravity cease to produce finite answers. Infinity appears. At first glance, infinity may sound like merely a very large number. In mathematics, however, infinity is something quite different. It is often a warning sign. Whenever physicists encounter infinities in their equations, experience suggests they should be cautious. The equations may not be describing reality itself. Instead, they may be announcing that the theory has reached the edge of its usefulness. There is a familiar analogy. Suppose someone possessed a map of an entire continent drawn with extraordinary precision. Roads, rivers, mountains, forests, and cities all appeared exactly where they should. Then one day they reached the coastline. The map ended abruptly, not because the world ended there, but because the map maker had never surveyed beyond it. The blank edge did not represent reality. It represented the limit of the map. Many physicists suspect singularities serve a similar role. They may not be physical places at all. They may simply mark the point where general relativity no longer provides a complete description of nature. The reason becomes clearer when another great pillar of modern science enters the story: quantum mechanics. If general relativity governs the largest structures in existence, quantum mechanics governs the smallest. It describes atoms, electrons, photons, and the strange probabilities that define the microscopic world. Unlike relativity, which portrays space and time as smooth and continuous, quantum theory reveals a universe filled with uncertainty. Particles behave like waves. Energy comes in discrete packets. Events can only be predicted statistically. The deeper scientists explored this tiny realm during the 20th century. The stranger it became. Yet despite its peculiar behavior, quantum mechanics proved extraordinarily successful. It predicted the existence of antimatter. It explained the structure of atoms. It led to semiconductors, lasers, magnetic resonance imaging, and nearly every modern electronic technology. Its predictions have been verified to astonishing precision. So humanity possesses two magnificent theories. One governs the very large. The other governs the very small. For most situations, they coexist peacefully. The orbit of Earth around the Sun requires general relativity only as a tiny correction. The chemistry inside a living cell depends overwhelmingly on quantum mechanics. Neither theory interferes significantly with the other. Black holes change that. Near the center of a black hole, matter is compressed into unimaginably small regions, while gravity simultaneously becomes unimaginably strong. Both theories become equally important, and this is precisely where they refuse to cooperate. General relativity assumes that space and time remain smooth. Quantum mechanics suggests that at extremely tiny scales, smoothness itself may disappear, instead of a perfectly continuous fabric. Space could possess an underlying quantum structure. Somewhat as a seemingly smooth beach is actually composed of countless grains of sand when viewed closely. No one yet knows whether this picture is correct, but many approaches to quantum gravity suggest something like it. The scale where this hidden structure would become important is unimaginably small. Physicists call it the Planck length. It measures about 1.61035 meters. To appreciate how tiny this is, consider that an atom is already extraordinarily small compared with everyday experience. The Planck length is smaller than an atom by roughly 25 orders of magnitude. if an atom were enlarged until it spanned the entire observable universe. The Planck length would still remain microscopic within that enormous scale. Below this distance, the familiar concepts of space and time themselves may lose their ordinary meaning. This is not because scientists have observed such behavior directly. Rather, every attempt to combine quantum mechanics with general relativity points toward the conclusion that something fundamentally new must occur there. The singularity predicted by classical relativity lies far beyond this boundary. If quantum effects become dominant before infinite density is reached, then the collapse of matter could unfold very differently than Einstein's equations alone predict. This possibility has inspired decades of research. Some theories suggest that quantum pressure might halt collapse before a singularity forms. Others propose that space-time acquires an entirely new geometry. Still others envision microscopic loops, vibrating strings, or discrete quantum building blocks replacing the smooth continuum we ordinarily experience. These ideas differ dramatically from one another, yet they share one important conclusion: the classical singularity may never actually exist. This distinction is essential. The existence of black holes is supported by overwhelming observational evidence. The existence of singularities is not observed directly. It is inferred from equations that almost certainly become incomplete under the extreme conditions inside a black hole. That difference leaves room for profound possibilities. If there is no singularity, then what occupies the deepest interior? Does collapsing matter stabilize into some unknown quantum state? Does it rebound? Does space itself undergo a transformation? Or does an entirely new region of space-time merge beyond what our current theories can describe? At present, no experiment can answer these questions directly. The event horizon ensures that whatever occurs inside remains hidden from outside observers. Astronomers can study the edge with increasing precision, but the interior remains inaccessible. It is one of the rare places where the greatest achievements of modern science meet an equally great silence. And yet history offers an encouraging lesson whenever two highly successful theories disagree. The conflict rarely ends with one theory simply defeating the other. Instead, a deeper framework usually emerges, revealing that both were incomplete glimpses of a richer reality. Newton was not wrong. His theory became part of Einstein's larger picture. Classical mechanics was not discarded. It became a special case within quantum physics. Perhaps the same will someday happen here. General relativity and quantum mechanics may both become chapters within an even deeper theory that has not yet been discovered. If that theory finally explains what replaces the singularity, it may also answer one of the most remarkable questions ever asked. Not merely what happens inside a black hole, but whether the collapse of one universe can become the birth of another. The story begins not with a telescope, nor with a collapsing star, but with a simple question. If gravity is not a force pulling objects through space, as Isaac Newton believed, but instead a consequence of space itself bending under the presence of mass, what would happen if enough mass were gathered into one place? When Albert Einstein published his theory of general relativity in 1915, he had transformed humanity's understanding of gravity. Space and time were no longer passive stages upon which the universe performed its motions. Together they formed a single fabric, flexible enough to curve, stretch, and evolve. Matter told space-time how to curve. Curved space-time told matter how to move. The equations describing this relationship were beautiful, compact, and astonishingly complex. Einstein himself did not know every solution they contained. Within weeks of their publication, a young German physicist serving on the Eastern Front during the First World War began exploring them. His name was Karl Schwarzschild, working under extraordinarily difficult conditions, surrounded by the realities of war rather than the quiet halls of a university. Schwarzschild discovered the first exact solution to Einstein's equations. He imagined something remarkably simple: a perfectly spherical mass, no rotation, no electric charge, nothing except gravity. The mathematics led him to an unexpected result. If enough mass occupied a sufficiently small radius, space-time became so severely curved that a boundary appeared beyond which no outward path existed. Today, this distance is called the Schwarzschild radius. Anything compressed inside this radius would possess an event horizon. At the time, however, neither Schwarzschild nor Einstein regarded this as a likely feature of the real universe. The equations suggested something extraordinary. But nature often allows mathematics that never becomes reality. After all, Equations can describe ideal circles, perfectly smooth surfaces, and infinitely long lines, even though such objects do not exist physically. Many physicists assumed the same would prove true here. The strange boundary appeared to be a mathematical curiosity rather than an astronomical object. Einstein himself remained skeptical. Throughout much of his life, he believed nature would somehow prevent matter from collapsing so completely. The idea of a star compressing itself into an invisible prison of gravity seemed almost unreasonable. For decades, few scientists devoted serious attention to the problem. Then astronomy quietly began changing. In the early 20th century, our understanding of stars underwent a revolution. For thousands of years, stars had appeared eternal. They rose each night with comforting regularity, their patterns changing only over centuries. Gradually, however, astronomers discovered that stars are not permanent lights. They are living systems. They are born from cold clouds of gas. They spend millions or billions of years converting hydrogen into helium. Eventually, they exhaust the nuclear fuel that supports them against gravity. Once this life cycle became understood, an unavoidable question followed. What determines the final fate of a dying star? During the 1930s, a young Indian physicist named Subrahmanyan Chandrasekhar began calculating the answer while travelling by ship from India to England. Using the newly developed principles of quantum mechanics, he studied white dwarfs, the dense remnants left behind by sun-like stars. His calculations revealed something unexpected. There exists a maximum mass beyond which a white dwarf cannot remain stable. If enough matter is added, gravity inevitably overwhelms the quantum pressure supporting it. Today, this boundary is known as the Chandrasekhar limit. The conclusion was unsettling. Not every star could end peacefully. Some were simply too massive. When Chandrasekhar presented his results, he encountered strong resistance. One of the most respected astronomers of the era, Arthur Eddington, publicly criticized the idea. The notion that gravity could continue collapsing a star without limit seemed unacceptable. Many scientists preferred to believe that some unknown physical process would intervene. History would eventually prove Chandrasekhar correct, but that confirmation would take decades. As nuclear physics advanced after the Second World War, astronomers gained a clearer picture of stellar evolution. Massive stars burn their fuel rapidly. They produce heavier and heavier elements within their cores. Eventually, fusion reaches iron. Unlike lighter elements, iron cannot release additional energy through fusion. The star loses its source of outward pressure. Gravity suddenly gains the upper hand. The collapse that follows is astonishingly swift. Within seconds, the core contracts dramatically. Temperatures soar into the billions of degrees. Matter is compressed beyond anything found naturally elsewhere. The outer layers explode outward in a supernova. For a brief time, a single dying star can outshine an entire galaxy. The explosion enriches surrounding space with elements such as oxygen, silicon, calcium, and iron. Every atom of gold in a wedding ring, every atom of iodine in the human body, every atom of calcium in our bones owes its existence to generations of stars that lived and died long before the solar system formed, even before black holes enter the story. Stellar collapse has already shaped everything familiar to us. Yet some stellar cores survive the explosion. If the remaining mass is modest, a neutron star forms. If it is greater still, collapse continues. This time, nothing known stops it. During the 1960s, theoretical work by Roger Penrose and Stephen Hawking transformed the discussion. Using sophisticated mathematical techniques, they demonstrated that under remarkably general conditions, Einstein's equations predict gravitational collapse leading towards singularities. Their singularity theorems did not prove that physical infinities exist in nature. Rather, they show that if general relativity remains valid under such extreme conditions, singularities become unavoidable consequences. This shifted the conversation dramatically. The problem was no longer whether black holes could exist. The problem became understanding what happened inside them. At almost the same time, astronomy began finding compelling observational evidence. Powerful X-ray sources appeared in the sky. Invisible companions tugged visibly on neighbouring stars. Galactic centres displayed motions requiring enormous unseen masses. One by one, observations aligned with theoretical expectations. The mathematical curiosity imagined by Schwarzschild gradually became an astronomical certainty. Then came one of the greatest scientific triumphs of the 21st century. In 2015, gravitational waves produced by merging black holes were detected directly for the first time. Einstein had predicted their existence exactly 1 century earlier. The signal matched theoretical calculations with extraordinary precision. What had once existed only as mathematics had announced itself across more than 1 billion light-years of space. 4 years later, another milestone arrived. The Event Horizon Telescope revealed the shadow surrounding the supermassive black hole in the galaxy M87. For the first time, humanity could compare a real black hole with predictions made decades earlier. Again, Einstein's theory succeeded. Remarkably, the greatest challenge to general relativity has never come from these observations. Outside black holes, Einstein's equations continue to perform with breathtaking accuracy. The challenge comes from somewhere no telescope can see. The deeper the equations are followed toward the center, the more confidently they predict their own breakdown. It is an extraordinary situation, a theory capable of describing galaxies, gravitational waves, and the evolution of the cosmos with astonishing precision ultimately points toward a place where it can no longer describe reality at all. Rather than diminishing Einstein's achievement, this makes it even more profound. His equations did not merely explain gravity, they illuminated the location where an even deeper theory must someday begin. That frontier lies hidden beyond every event horizon, where the legacy of general relativity ends not with certainty, but with one of the greatest unanswered questions in modern science. By the middle of the 20th century, black holes had changed from mathematical possibilities into astronomical realities. Yet another surprise was waiting. For a long time, astronomers assumed black holes would be relatively rare. After all, they form only when the most massive stars exhaust their fuel and collapse under their own gravity. Such stars are uncommon, living fast and dying young. It seemed reasonable to picture black holes as isolated remnants scattered across the Milky Way, quietly drifting through the darkness. Instead, the universe revealed something far more remarkable. The deeper astronomers looked into space, the more often black holes appeared. Not only were they found throughout our own galaxy, but evidence suggested that nearly every large galaxy possessed one at its center, and these were unlike anything produced by ordinary stellar collapse. They were enormous. Our Sun contains almost all the mass of the solar system. Jupiter, despite being the largest planet, is only about 1,000th as massive as the Sun. The black hole at the center of the Milky Way outweighs our Sun by approximately 4 million times. Other galaxies contain central black holes measuring hundreds of millions or even tens of billions of solar masses. Some are so immense that the orbits of nearby stars take centuries to complete. The question naturally followed: how could anything become so large? Unlike stars, black holes do not shine by producing energy through nuclear fusion. They grow in quieter ways. Gas drifting through a galaxy may gradually spiral inward. Entire stars occasionally wander too close, pulled apart by tidal forces before disappearing beyond the event horizon. Black holes themselves can merge, combining their masses into larger objects. These processes continue over billions of years. The result is a slow but persistent cosmic accumulation. Yet growth alone may not explain everything. Many supermassive black holes already existed when the universe was surprisingly young. Observations by modern space telescopes have revealed quasars whose light began its journey less than 1 billion years after the Big Bang. Their central black holes were already billions of times more massive than the Sun. This presents astronomers with another puzzle. The universe may simply not have had enough time for ordinary growth processes to build such enormous objects. Perhaps they formed from unusually massive clouds of gas. Perhaps they experienced periods of extraordinarily rapid feeding. Or perhaps some began their lives in ways that astronomers have not yet fully understood. The answer remains uncertain. Once again, black holes invite us toward questions rather than conclusions. What is certain is that these giants profoundly influence the galaxies around them. At first, this seems counterintuitive. Compared with an entire galaxy, even a supermassive black hole occupies an incredibly tiny region. If the Milky Way were enlarged until it stretched across North America, the event horizon of its central black hole would still be smaller than many cities. How can something so compact affect hundreds of billions of stars spread across 100,000 light-years? The influence comes not from size, but from energy. As gas falls toward a supermassive black hole, it rarely disappears immediately. Instead, it forms a rapidly rotating accretion disk. The particles within this disk travel at astonishing speeds, colliding with one another countless times each second. The friction generated by these collisions heats the gas to extraordinary temperatures. In some cases, the disk becomes brighter than every star in its host galaxy combined. Such objects are known as quasars. During the 1960s, quasars puzzled astronomers because they appeared almost star-like through telescopes, yet emitted unimaginable amounts of energy. Only gradually did researchers realize that these brilliant beacons were powered not by stars, but by matter falling into supermassive black holes. Ironically, the brightest objects in the observable universe owe their brilliance to regions surrounding the darkest objects in existence. Even more astonishing are the enormous jets that some black holes produce. Powerful magnetic fields can channel a small fraction of infalling material into narrow streams, traveling outward at nearly the speed of light. These jets emerge from opposite sides of the black hole and can extend for hundreds of thousands, sometimes even millions, of light years. They plow through surrounding gas, heating it and preventing portions from cooling enough to form new stars. In this way, a single supermassive black hole can influence the future evolution of an entire galaxy. The relationship appears almost paradoxical. Galaxies help feed black holes. Black holes help regulate galaxies. Neither evolves entirely independently of the other. This realization transformed astronomy. Black holes were no longer viewed as isolated cosmic oddities. They became central participants in the evolution of the universe. The Milky Way itself bears witness to this quiet partnership. At its center lies Sagittarius A, a supermassive black hole currently living a relatively peaceful existence. It consumes only small amounts of gas compared with the spectacular quasars seen elsewhere. Even so, careful observations over several decades have tracked individual stars racing around this invisible object. One star, known as S2, completes an orbit in about 16 years. Near its closest approach, it reaches speeds exceeding several million kilometers per hour. Only an extraordinarily compact concentration of mass can account for such motion. These measurements provided some of the strongest evidence that Sagittarius A truly is a supermassive black hole. In recognition of this work, the 2020 Nobel Prize in Physics honored research that established black holes as robust components of modern astrophysics. Yet despite all these achievements, a curious limitation remains. Everything astronomers have learned concerns the influence black holes exert on their surroundings. We observe stars circling them. We observe gas heating around them. We observe jets streaming away from them. We observe gravitational waves produced as they merge, but the interior remains hidden. It is rather like studying an ancient tree by examining its roots, branches, and leaves while never seeing the living cells beneath its bark. The outward behavior tells us much. The deepest processes remain concealed. This hidden interior becomes even more intriguing when viewed on the largest possible scale. The observable universe contains hundreds of billions of galaxies. Each large galaxy likely contains at least one supermassive black hole. Many smaller black holes also populate galaxies, formed through the deaths of massive stars. The total number of black holes may therefore be almost beyond comprehension. If every one of them contains an inaccessible interior where our current theories fail, then these hidden regions collectively represent one of the greatest unknown territories in science. The night sky suddenly acquires a new dimension. Every faint galaxy becomes more than a collection of stars. At its center may lie an unseen doorway into physics we have not yet mastered. Whether those interiors contain singularities, exotic quantum states, or something even stranger remains unknown. But the sheer abundance of black holes changes the nature of the mystery. This is no longer a question about a handful of rare objects. It is a question repeated throughout the cosmos, perhaps hundreds of billions of times, and that repetition carries an extraordinary implication. If black holes truly do something unexpected beyond their event horizons, then whatever that process may be is not an obscure curiosity. It could be one of the most common, and yet most hidden, phenomena in the entire universe. That realization brings us naturally to the heart of our journey, for despite everything astronomy has learned about black holes, one boundary still separates established knowledge from profound uncertainty. It is the silent horizon beyond which observation ends. Mathematics grows uncertain, and some of the boldest ideas in modern cosmology begin. There is a remarkable pattern that appears throughout the history of astronomy. The more carefully humanity observes the universe, the farther the boundary of certainty retreats. Ancient astronomers believed the stars were fixed upon a crystalline sphere, until better observations revealed a far larger cosmos. The Milky Way once seemed to be the entire universe, until distant galaxies emerged from the darkness, even the expansion of the universe. Now, one of the foundations of cosmology was unknown little more than a century ago. Each discovery answered old questions while uncovering deeper ones. Black holes continue this tradition. By now, astronomers understand a great deal about how black holes form, how they grow, and how they influence the galaxies around them. General relativity predicts their external behavior with extraordinary precision. Every new observation, from stellar orbits to gravitational waves, strengthens that picture, and yet all of this knowledge stops at one invisible boundary: the event horizon. It is difficult to think of another place in science where the line between the known and the unknown is drawn so sharply. The event horizon is not a wall, it is not a solid shell. Nothing special announces its presence to an observer who falls freely across it. According to Einstein's theory, someone crossing the horizon of a sufficiently large black hole might notice nothing unusual at that exact moment. The sky would still surround them. The stars would still shine. The laws of physics in their immediate surroundings would appear perfectly ordinary. Only later would they discover that every possible future path leads deeper inward. The event horizon is therefore not a physical barrier. It is a causal one. It separates events that can still influence the outside universe from those that can never do so again. This simple idea has extraordinary consequences. Suppose an astronaut carried a powerful flashlight while drifting toward a supermassive black hole. As long as the astronaut remained outside the event horizon, light from the flashlight could still travel outward, eventually reaching distant observers. The closer the astronaut approached the horizon, however, the more severely that light would be stretched. Its wavelength would grow longer. Its color would shift steadily toward red. Eventually it would move beyond visible light into infrared, then radio waves, becoming increasingly difficult to detect. This phenomenon is known as gravitational redshift. To a distant observer, the astronaut would appear to slow down. The signals arriving from the flashlight would become weaker and farther apart. The astronaut's clock would seem to run more and more slowly. From far away, it would almost appear as though the astronaut never quite reached the horizon at all. Instead, the image would gradually fade into darkness. Yet this is only half of the story. From the astronaut's own perspective, nothing unusual happens to time. Their watch continues ticking normally. Their heartbeat remains steady. They cross the event horizon after a perfectly finite amount of personal time. This apparent contradiction often confuses those encountering relativity for the first time. How can one observer see the crossing never completed while another experiences it naturally? The answer lies in one of Einstein's deepest insights. Time is not universal. Different observers can legitimately measure different intervals depending upon gravity and motion. Neither perspective is privileged. Both are correct within their own frame of reference. This strange feature of relativity hints at something even more profound. The event horizon is not simply hiding a location. It is separating different descriptions of reality. Outside observers can never directly verify what occurs after crossing. Inside, observers cannot return to report their experiences. Nature itself prevents the comparison. This is where the central mystery begins. If no information can escape from beyond the horizon, what becomes of everything that falls inside? At first, the answer appears straightforward. Matter continues inward toward the singularity. Its story simply ends there. For many decades, this was considered the natural conclusion of Einstein's theory. But during the second half of the 20th century, another unexpected complication emerged. It began with a deceptively simple question. What is information? In everyday life, information seems almost abstract. The arrangement of letters on a page, the sequence of notes in a melody, the pattern of molecules inside a living cell. Modern physics, however, treats information as something remarkably fundamental. Every particle possesses measurable properties: mass, electric charge, momentum, quantum states. Together, these properties describe the physical condition of a system. According to quantum mechanics, information about these states should never simply vanish. It may become extraordinarily difficult to reconstruct. It may spread throughout the environment, but complete destruction of information appears incompatible with the basic principles of quantum theory. Black holes challenge this principle. Suppose an encyclopedia falls into a black hole, then a library, then an entire planet containing every work of literature humanity has ever written. From outside the event horizon, All of that complexity appears to disappear forever. Only the black hole's mass, electric charge, and angular momentum remain measurable. Everything else seems erased. This observation eventually became known as the black hole information paradox. The paradox grew even deeper after Stephen Hawking made one of the most influential discoveries in theoretical physics. By combining quantum mechanics with curved space-time, Hawking found that black holes are not completely black. Instead, they should emit an extremely faint form of thermal radiation. Today it is called Hawking radiation. The process is subtle. Quantum fields naturally fluctuate even in empty space. Near the event horizon, these fluctuations can lead to the gradual escape of energy. Over unimaginably long periods, a black hole may slowly lose mass. If enough time passes, it could eventually evaporate completely. This discovery transformed the discussion. Previously, matter simply disappeared behind the horizon. Now the black hole itself might disappear as well. If the black hole ultimately evaporates into featureless thermal radiation, where has the original information gone? Was it destroyed? Hidden? Encoded somehow within the outgoing radiation? Transferred elsewhere? No consensus exists. This is not a minor technical difficulty. It strikes at the foundations of modern physics. General relativity and quantum mechanics, each extraordinarily successful in its own domain, appear to offer incompatible answers. One suggests information may effectively vanish into the singularity. The other insists that information must always survive. For decades, some of the world's leading physicists have debated this problem. Ideas such as black hole complementarity, holography, quantum entanglement, firewalls, and soft quantum hair have all been proposed to resolve different aspects of the paradox. Some have gained significant support. Others remain controversial. None has been universally accepted. What makes this debate especially remarkable is that it extends far beyond black holes themselves. If information can truly be destroyed, quantum mechanics may require fundamental revision. If information cannot be destroyed, then our picture of black hole interiors must be incomplete. Either outcome reshapes our understanding of reality, and this is precisely where the idea of black holes creating universes quietly enters the conversation. If collapsing matter does not terminate in a singularity, perhaps information is not lost at all. Perhaps it continues its existence within a new expanding region of space-time, not because anyone has observed such a process, not because it has been proven, but because, among the many possibilities being explored, it offers one potential path around a mystery that neither of our greatest theories has yet fully resolved. The event horizon, once thought to mark the end of the story, becomes something else entirely. Not a conclusion, not even necessarily a prison, but a veil behind which one of the deepest unanswered questions in all of science continues to unfold. If the interior of a black hole cannot be observed directly, how can science make progress at all? At first, this seems like an impossible situation. Astronomy has always relied on light. Every telescope, from Galileo's simple refractor to the James Webb Space Telescope, ultimately studies photons that have travelled across space, whether those photons arrive as visible light. Radio waves, infrared radiation, or X-rays, they all carry information from distant objects. A black hole appears to deny astronomy its most valuable source of evidence. Nothing that crosses the event horizon can send light back out, yet science has found another path. Rather than observing what happens inside a black hole, astronomers examine everything that happens around one. It is a little like studying an invisible mountain by watching the rivers that flow around it. The mountain itself remains hidden in thick cloud, but the water reveals its shape, the paths of the rivers, the direction of the currents, and the speed of the flow all carry information about something that cannot be seen directly. Black holes reveal themselves in much the same way. Every nearby star, every cloud of gas, every burst of radiation becomes part of the evidence. One of the clearest examples comes from the stars orbiting Sagittarius A, the supermassive black hole at the center of our galaxy. For decades, teams of astronomers patiently measured their positions. Year after year, orbit after orbit. The changes were tiny, requiring extraordinary precision. Yet as more observations accumulated, a remarkable picture emerged. Some stars were moving at several thousand kilometers per second. Their paths curved sharply around an object that emitted almost no light. By applying Newton's laws, and later Einstein's corrections, astronomers calculated the mass required to produce those orbits. The answer was unavoidable. Roughly 4 million suns had to be concentrated inside a region smaller than our solar system. No known collection of ordinary stars could remain stable under such conditions. Only a supermassive black hole fit every observation simultaneously. This illustrates an important principle in astronomy. The strongest conclusions rarely come from a single observation. They emerge when many independent observations all point toward the same explanation. Black holes satisfy this standard exceptionally well. The evidence continues with accretion disks. As gas spirals inward, it accelerates to extraordinary speeds. Near the event horizon of a supermassive black hole, matter may orbit at a significant fraction of the speed of light. At such velocities, collisions between particles generate enormous amounts of heat. Temperatures climb into the millions of degrees. Atoms become completely ionized. The resulting plasma shines intensely in X-rays. Space telescopes such as Chandra and XMM Newton have observed these brilliant emissions throughout the universe. The detailed spectra of the X-rays reveal even more. Iron atoms within the disk produce characteristic emission lines. Near a black hole, however, these lines become broadened and distorted. General relativity predicts exactly this behavior. Light escaping from regions of extreme gravity loses energy. Rapid orbital motion shifts wavelengths in opposite directions depending on whether the gas is moving toward or away from us. The combined effect creates signatures unlike anything found elsewhere. Again, observation and theory agree remarkably well. Yet perhaps the most dramatic breakthrough arrived in a completely different form. Not through light, but through gravity itself, for a century after Einstein proposed general relativity. Gravitational waves remained purely theoretical. The equations predicted that accelerating massive objects should produce ripples in space-time. Somewhat as a stone dropped into a quiet pond creates expanding waves across the surface. The difficulty was scale. By the time these ripples reached Earth, they would be unimaginably small. A passing gravitational wave changes distances by less than the diameter of a proton across instruments several kilometers long. Detecting such tiny distortions seemed almost impossible. Then, in September 2015, two enormous observatories separated by thousands of kilometers recorded the same faint signal. It lasted only a fraction of a second. Its frequency steadily increased before abruptly ending. Physicists quickly recognized the pattern. Two black holes had been orbiting one another for millions of years. As they lost energy through gravitational radiation, they spiraled ever closer together. During the final moments, they completed dozens of orbits each second. Then they merged into one larger black hole. The energy released during that final instant exceeded the combined light output of every star in the observable universe. Not as light, as gravitational waves, those ripples travelled across more than 1 billion light-years before gently passing through Earth. The detectors measured them exactly as Einstein's theory predicted. Since then, gravitational wave observatories have detected many more mergers. Some involve neutron stars, others involve black holes of different masses. Each detection provides another opportunity to test general relativity under the most extreme conditions nature offers. So far, Einstein continues to pass. Remarkably, these observations also tell us something about what they cannot tell us. Every gravitational wave signal originates outside the event horizons of the merging black holes. The end spiral, the collision, the settling of the final black hole, all of these processes occur within regions still described by observable physics. The interior remains hidden. Even gravity, which carries information across billions of light-years, does not reveal what lies beyond the horizon. Computer simulations have therefore become an essential partner to observation. Modern supercomputers solve Einstein's equations numerically, following the evolution of space-time itself. Entire regions of curved geometry are divided into millions or billions of computational elements. Each tiny region evolves according to the equations of general relativity. The calculations demand enormous computing power. Some simulations require weeks of continuous operation on powerful supercomputers. Their purpose is not to invent new physics. Rather, they predict what known physics should produce. The simulated gravitational waves can then be compared directly with observations. The agreement has been extraordinary. Yet something fascinating happens whenever these simulations approach the deepest interior. The mathematics becomes increasingly uncertain. Near the singularity predicted by classical relativity, numerical methods struggle because the equations themselves approach infinite values. Researchers often remove the singular region from the calculations entirely. focusing instead on the observable exterior where the predictions remain reliable. This practice reflects an important distinction. The simulations successfully describe what astronomers can measure. They do not resolve the ultimate fate of matter inside the black hole. That question still belongs to theories extending beyond classical relativity. Increasingly, astronomers hope that subtle observational clues might someday distinguish between competing ideas. Could quantum effects slightly alter the gravitational waves produced during black hole mergers? Might the final vibrations, sometimes called the ring down, contain tiny deviations from Einstein's predictions? Could future detectors become sensitive enough to notice them? These possibilities are being actively investigated. The next generation of observatories, including larger ground-based detectors and planned space missions such as LISA, promises measurements far more precise than those available today. Perhaps the smallest irregularity will reveal where general relativity begins to give way to something deeper, or perhaps Einstein's theory will continue succeeding, pushing the frontier even closer to the hidden interior. Either outcome would be valuable. Science advances not only by discovering new phenomena, but also by carefully confirming where existing theories remain correct. Every observation narrows the range of possibilities. Every measurement removes some ideas while strengthening others. And yet, after decades of increasingly sophisticated observations, one fact remains unchanged. Everything we know with certainty concerns the exterior. The greatest mystery still waits beyond the horizon. To proceed farther, observation alone is no longer enough. The journey now enters a different landscape, where evidence continues to guide us. But multiple explanations compete to describe what the evidence may ultimately mean. Once observation reaches its limit, theory takes on a different role. It no longer describes what has already been seen. Instead, it explores what remains possible without contradicting the evidence. This distinction is one of the defining strengths of science. A good scientific theory is not a free exercise of imagination. It must begin with what is already known. It must agree with every successful observation that came before. Only then may it venture into territory that experiments have not yet reached. Black holes present exactly this challenge. Astronomers know they exist. They know how they bend light. They know how they merge. They know how they shape galaxies. But beyond the event horizon, several different pictures remain consistent with everything humanity has observed so far. Some of these ideas are widely accepted in part. Others remain highly speculative. Each attempts to answer the same fundamental question: what replaces the singularity predicted by classical general relativity? The oldest answer is also the simplest. According to classical general relativity alone, nothing replaces it. Matter continues collapsing until all paths lead toward a singularity, where density and space-time curvature become infinite. This picture follows directly from Einstein's equations under ideal conditions. It requires no additional physics. For many decades, this remained the standard description. Its greatest strength is simplicity. It extends a theory that already works extremely well. Its greatest weakness is equally obvious. Infinite quantities almost always signal that the theory has reached its limit. Few physicists believe nature literally contains infinities. Instead, many suspect that some new physical process intervenes before they can form. This brings us to quantum gravity. Quantum gravity is not one theory. It is the collective name for attempts to unite quantum mechanics with general relativity into a deeper framework. Several major approaches exist. Each proposes a different picture of space-time at the smallest possible scales. One of the oldest and best-known approaches is string theory. Instead of treating elementary particles as point-like objects with no size, string theory proposes that the fundamental ingredients of nature are unimaginably tiny vibrating strings. Different patterns of vibration correspond to different particles: electrons, photons, quarks. Even the particle that would carry gravity, if it exists, emerges naturally within the mathematical framework. One attractive feature of string theory is that gravity becomes compatible with quantum mechanics. In principle, singularities may be softened or avoided because matter is no longer infinitely concentrated. Yet despite decades of development, string theory has not produced direct experimental evidence. Its mathematics is rich and elegant. Its physical predictions remain difficult to test. Another major approach takes a very different path. Loop quantum gravity suggests that space-time itself possesses a microscopic structure. Rather than being perfectly continuous, Space may consist of tiny discrete units woven together into an intricate network. From a distance, the fabric appears smooth, much as a digital photograph appears continuous until examined pixel by pixel. At extremely small scales, however, continuity gives way to individual building blocks. Within this picture, gravity may behave differently under extreme compression. Instead of allowing infinite density, quantum effects could generate a powerful resistance. Collapse might eventually halt. Some versions even predict a rebound. Matter falling inward could transition into an expanding region of space-time. This possibility leads naturally toward one of the most fascinating ideas in modern cosmology: the black hole bounce. In this scenario, collapse never reaches an actual singularity. Instead, quantum gravity reverses the process. From the viewpoint of the collapsing matter, an entirely new expansion begins. Whether that expanding region remains connected to our universe or becomes causally separated depends upon the specific mathematical model. Here we must distinguish carefully between observation and hypothesis. No telescope has observed such a bounce. No experiment has confirmed it. It remains a theoretical possibility motivated by attempts to avoid singularities while preserving known physical laws. Another family of ideas involves wormholes. The concept entered physics through solutions to Einstein's equations describing bridges connecting distant regions of space-time. Popular culture often portrays wormholes as shortcuts across the cosmos. Reality is considerably more uncertain. Many mathematical wormhole solutions appear unstable. Some require forms of matter possessing negative energy densities not known to exist in macroscopic quantities. Whether naturally traversable wormholes can actually form remains an open question. Even so, wormholes illustrate an important lesson. Einstein's equations permit geometries far stranger than everyday experience suggests. Black holes may therefore contain structures more complicated than a simple inward collapse. Perhaps the most directly relevant idea for our documentary comes from cosmological models, proposing that black holes create new universes. Several physicists have explored versions of this possibility over the past few decades. Although the details differ, the central concept is surprisingly consistent. As matter collapses toward conditions where classical relativity predicts a singularity, quantum gravity prevents infinite compression. Instead, a new region of expanding spacetime forms. To observers inside that expanding region, the process could resemble the birth of an entirely new universe. Remarkably, the inhabitants of such a universe might never know they originated inside another black hole. Their observable cosmos would possess its own space, its own time, its own galaxies, its own history stretching back toward what they would interpret as a beginning. The parent universe would remain forever inaccessible beyond their own cosmic horizon. This resemblance has inspired intriguing comparisons between black hole interiors and the early stages of our own universe. The comparison should not be misunderstood. Scientists have not demonstrated that our universe emerged from a black hole. There is no observational proof supporting that conclusion. Instead, certain mathematical similarities have encouraged researchers to investigate whether such a connection might exist. Another proposal extends the idea even further. Theoretical physicist Lee Smolin suggested a concept known as cosmological natural selection. The hypothesis begins with an observation. Universes capable of producing many black holes would naturally generate more daughter universes if black holes truly give birth to new cosmic regions. Over many generations, physical constants favoring abundant black hole formation might become increasingly common. The process resembles biological evolution in a highly abstract sense, not because universes are alive, not because they compete consciously, but because certain properties become statistically more frequent through repeated reproduction. It is a bold idea. It also remains speculative. No evidence currently demonstrates that universes reproduce in this manner. Nevertheless, the hypothesis illustrates how black holes could influence cosmology on scales far beyond individual galaxies. There are also more conservative possibilities. Perhaps quantum gravity resolves singularities without creating new universes. Perhaps information escapes through subtle quantum processes that remain hidden within Hawking radiation. Perhaps space-time develops structures unlike anything currently imagined. Science has not yet chosen among these possibilities because nature has not yet supplied enough evidence. This uncertainty is not a weakness. It is an honest reflection of where knowledge presently stands. We therefore arrive at 4 distinct categories. Observed facts. Black holes exist. They possess event horizons. They merge. They influence galaxies. Measured evidence. gravitational waves, orbital motions, accretion disks, direct imaging of black hole shadows, accepted theory. General relativity accurately describes gravity outside black holes. Quantum mechanics accurately describes microscopic physics. Open hypotheses, quantum gravity, black hole bounces, universe creation, cosmological natural selection, wormhole interiors. Each belongs in its proper place. Keeping these categories separate allows curiosity to flourish without sacrificing scientific integrity. And among all these competing ideas, one possibility quietly stands apart, not because it has been proven, but because if it were true, its consequences would extend far beyond black holes themselves. It would transform our understanding of cosmic beginnings. It would suggest that every collapsing star may contribute to an endless chain of creation. The question is no longer simply what happens inside a black hole. The question becomes what kind of universe might emerge if one of these remarkable ideas turned out to be correct. Suppose, for a moment, that the singularity predicted by classical general relativity never actually forms, not because Einstein's theory was incorrect, but because it reaches the edge of its domain before infinite density can occur. Suppose that, under conditions where gravity becomes inseparable from quantum physics, collapse simply changes character. The inward journey continues, but instead of ending at an infinitely small point, it becomes the beginning of something entirely new. This is one of the most intriguing possibilities explored by several approaches to quantum gravity. It remains a hypothesis, yet it is a hypothesis built upon a careful question. What if nature never allows infinities at all? Throughout physics, infinities have often disappeared when deeper theories emerged. Classical electromagnetism struggled with the energy of point particles until quantum theory provided a more complete framework. Newtonian gravity appeared perfectly adequate until Einstein revealed that gravity was actually the geometry of space-time. Again and again, infinities have marked places where understanding was incomplete rather than places where reality itself became impossible. If the same pattern holds inside black holes, then collapse may reach an extreme state without ever becoming truly infinite. The matter continues inward. Pressure increases beyond anything imaginable. Temperatures exceed those of the earliest moments after the Big Bang. Quantum effects, almost irrelevant throughout ordinary astrophysics, gradually become dominant. Eventually they may alter the very structure of space-time. Several theoretical models suggest that gravity itself could become effectively repulsive under such extraordinary conditions. This idea sounds surprising because gravity is always attractive in everyday life. Apples fall, planets orbit, galaxies pull upon one another. Yet quantum theories sometimes predict behaviors that have no everyday equivalent. Under sufficiently extreme circumstances, the geometry of space-time itself may resist further compression. Instead of an endless collapse, a transition occurs. The inward motion slows, stops, then reverses, not explosively, not like a conventional explosion sending debris back into our universe. Rather, the reversal unfolds within the hidden interior beyond the event horizon. From the perspective of the collapsing matter, space itself begins expanding. This expansion is not occurring into pre-existing emptiness. Instead, space is coming into existence as it expands. Curiously, this description resembles something already familiar. According to modern cosmology, the early universe did not expand into empty space. Space itself expanded. Every galaxy moved away from every other because the fabric connecting them stretched. There was no external container waiting to receive the expanding cosmos. The expansion created the distances themselves. If a similar process occurred inside a black hole, observers living within that expanding region might witness something astonishingly familiar. Their universe would begin in an extremely hot, dense state. Space would expand. Matter would cool. Particles would combine into atoms. Stars would eventually ignite. Galaxies would form. Over billions of years, complexity could emerge. To those observers, everything would appear entirely natural. Their measurements would describe an expanding universe with its own history. They would have no obvious reason to suspect that their cosmic beginning had any connection to a black hole existing elsewhere. In fact, they could never observe that parent universe directly. The event horizons separating the two regions would prevent any exchange of information. Their observable universe would be complete from their perspective. This leads to one of the most remarkable consequences of the hypothesis. The birth of a new universe would not resemble a bubble floating through an existing cosmos. Instead, It would possess its own independent space-time, its own clocks, its own distances, its own causal structure, from within. There would be no visible boundary marking where the parent universe ended. This idea requires a subtle shift in perspective. Ordinarily, we picture objects existing inside the universe. Stars, planets, black holes, galaxies, all occupy locations within the same cosmic arena. But if black holes generate new universes, then the relationship becomes hierarchical rather than spatial. A universe is not located somewhere inside its parent in the ordinary sense. Instead, it branches from the parent through a region inaccessible to outside observers. The geometry involved is difficult to visualize because our everyday intuition evolved within ordinary three-dimensional space. General relativity repeatedly reminds us that space-time is not constrained by ordinary intuition. It possesses structures that have no simple analogue in daily experience. This is why physicists rely upon mathematics rather than mental pictures alone. The equations often remain trustworthy long after imagination begins to struggle. Some researchers have noticed another intriguing similarity. The early universe appears remarkably smooth. When astronomers map the cosmic microwave background, the oldest light observable today, they find tiny temperature variations across the sky. But those variations are astonishingly small. The infant cosmos was extraordinarily uniform. Explaining this smoothness has long been one of cosmology's central challenges. The theory of cosmic inflation addresses much of this puzzle. According to inflation, the universe experienced an extremely rapid period of expansion during its earliest fraction of a second. Tiny quantum fluctuations were stretched across enormous distances, eventually becoming the seeds from which galaxies formed. If black hole interiors evolve into expanding universes, inflation could still occur within them. The new universe would possess its own internal history beginning with quantum gravity, followed by inflation, ordinary expansion, star formation, and cosmic evolution. The black hole origin would not replace the standard cosmological model. It would simply extend the story one step farther backward. Again, this remains speculative. There is presently no observation requiring such an origin. Standard cosmology successfully explains an enormous range of observations without invoking parent universes. The black hole scenario becomes interesting because it may eventually connect two great mysteries: the interior of black holes, the beginning of the universe. If both involve the same underlying quantum gravitational processes, then understanding one could illuminate the other. The idea also offers a fresh perspective on cosmic beginnings. The Big Bang is often misunderstood as an explosion occurring at a particular location. Modern cosmology rejects that picture. Every region of today's observable universe participated equally in the early expansion. There was no central point from which matter exploded outward. Likewise, if universes emerge from black holes, the birth of a daughter universe need not resemble matter erupting from a tiny hole into empty space. Instead, the entire space-time of the daughter universe unfolds according to its own internal geometry. Its beginning is everywhere within that universe at once. Perhaps the most profound implication concerns causality. Every observer experiences causes preceding effects within their own universe. Yet the origin of the universe itself lies beyond that internal chain. From the viewpoint of its inhabitants, the earliest measurable moment is simply the beginning of cosmic history. Whether another space-time preceded it may remain forever beyond observation. This mirrors our own situation. Today, astronomers can study the universe back to approximately 380,000 years after the Big Bang through the cosmic microwave background. They can infer conditions even earlier using nuclear abundances, gravitational theory, and particle physics. But the deepest beginning remains hidden behind conditions where known physics becomes incomplete. If our universe were born through processes inside a black hole, the observational barrier would naturally conceal that ancestry, not because evidence has been destroyed, but because space-time itself prevents direct access. This possibility is both humbling and exhilarating. Humbling because it reminds us how much may forever remain beyond observation. Exhilarating because it suggests that the apparent endings scattered throughout the cosmos might quietly participate in an endless process of creation. Every black hole could become the seed of another cosmic history. Every expanding universe could owe its existence to the collapse of a distant star or the growth of a supermassive black hole in another reality. Whether nature truly works this way remains unknown. Yet if it does, then the universe is no longer a single isolated story. It becomes part of a much larger narrative, one in which beginnings and endings are revealed to be different chapters of the same cosmic process. The next question follows almost inevitably. If universes can emerge from black holes, could the cosmos itself be filled with countless hidden universes, each forever invisible to all the others? If a single black hole could give rise to a new universe, then one remarkable possibility immediately follows. Perhaps it has happened more than once, not merely a handful of times across cosmic history, but countless times. The idea is both simple and deeply unsettling. Every large galaxy appears to contain at least one supermassive black hole. Every generation of massive stars leaves behind many smaller ones. Across the observable universe alone, the number of black holes is almost certainly enormous. If each possesses the potential to create another expanding region of space-time, then our universe might be only one branch within an immense and hidden family of universes. This possibility belongs to a broader collection of ideas known collectively as the multiverse. The word has become familiar in popular culture, often associated with parallel worlds where different versions of history unfold. Scientific discussions of the multiverse are considerably more restrained. Several independent areas of theoretical physics suggest that our observable universe may not represent all that exists. Importantly, these ideas do not all describe the same kind of multiverse. Some arise naturally from cosmic inflation, others emerge from string theory. Still others are motivated by quantum mechanics. The black hole hypothesis represents yet another possibility. Rather than imagining universes existing side by side in ordinary space, it envisions them connected through the birth and evolution of space-time itself. This distinction is crucial. When people hear the phrase "another universe," they often picture another cosmos floating somewhere beyond the edge of our own. Modern cosmology does not encourage that image. The observable universe already has no known edge in the ordinary sense. Its boundary marks the limit of how far light has travelled since the Big Bang, not the end of space itself. If daughter universes emerge inside black holes, they are not hidden behind distant galaxies. They are hidden behind causal boundaries. No amount of travel through ordinary space would ever reach them. Their separation is geometric rather than geographical. This idea can be approached through a familiar observation. Every observer possesses a cosmic horizon. Because light travels at a finite speed, there are regions of the universe so distant that their light has not yet reached Earth. Those regions certainly exist according to our best cosmological models, yet they remain permanently beyond direct observation. In this sense, astronomy already accepts that reality extends beyond what we can currently see. A daughter universe would represent a far more extreme version of the same principle. Its horizon would not merely be distant, it would be absolute. No signal could ever cross from one universe into the other after the new spacetime became causally independent. Each universe would experience itself as complete. Each would contain observers capable of constructing cosmological theories based entirely upon the evidence available within their own skies. Neither could directly verify the existence of the other. This naturally raises a philosophical question. Can science meaningfully discuss something that may never be observed? The answer depends upon what is meant by observation. Science often accepts the existence of entities before they are detected directly. Neptune was predicted mathematically before telescopes confirmed it. Gravitational waves were inferred from Einstein's equations a century before instruments became sensitive enough to detect them. The Higgs boson existed within theoretical physics decades before experiments at the Large Hadron Collider revealed it. Theories sometimes lead observation. Sometimes observation leads theory. Progress occurs when the two eventually meet. The challenge for black hole cosmology is that the meeting point remains uncertain. If daughter universes leave no observable traces within the parent universe, then the hypothesis becomes extraordinarily difficult to test. Many physicists therefore approach it with cautious interest. The idea is mathematically intriguing. Its scientific value depends upon whether it eventually produces predictions distinguishing it from competing explanations. This emphasis on testability remains essential. A beautiful idea alone is not enough. Nature must ultimately decide. Still, the possibility encourages us to reconsider one of cosmology's oldest questions. Why does our universe possess the particular properties that it does? The strength of gravity, the masses of elementary particles, the electric charge of the electron, the rate of cosmic expansion. These quantities appear finely balanced in ways that allow stars, galaxies, chemistry, and eventually life to emerge. Small changes to some of these constants could produce universes that look dramatically different. Some might collapse rapidly after their birth. Others might expand so quickly that galaxies never form. Still others might contain no long-lived stars at all. The reason our universe possesses its particular combination of physical constants remains one of modern science's deepest mysteries. Some explanations invoke chance, others seek hidden mathematical necessity. Black hole cosmology introduces another possibility. If each daughter universe inherits physical laws that differ slightly from those of its parent, then over many generations an immense diversity of universes could emerge. Most would remain barren. A few might accidentally possess conditions favourable for complex structure. Again, this is speculative. No observation currently demonstrates that physical constants change between hypothetical parent and daughter universes, yet the idea illustrates how black hole cosmology connects questions that once seemed unrelated. The life cycle of stars, the interiors of black holes, the origin of universes, the values of physical constants, all become parts of a single conceptual framework. Interestingly, astronomy has already taught us that the universe often builds complexity through repeated cycles. Stars manufacture heavy elements before scattering them into space. Those elements become new stars and planets. Planetary systems inherit material forged inside earlier generations of suns. Even our own bodies consist largely of atoms recycled through ancient stellar explosions. Nature rarely creates entirely from nothing. Instead, it transforms existing structures into new ones. Black hole cosmology extends this familiar pattern to the largest scale imaginable. Not merely stars giving rise to stars, but universes giving rise to universes. Whether this pattern truly exists remains unknown, yet it possesses an appealing continuity. The same cosmic processes that recycle matter across galaxies might, under extraordinary circumstances, recycle space-time itself. If so, creation would not be a singular event confined to one distant beginning. It would become an ongoing feature of reality. Every generation of stars would contribute, however indirectly, to the possibility of future universes. Every black hole would represent not only the end of one astrophysical story, but the potential beginning of another beyond observation. The night sky would acquire a new kind of depth. Every faint galaxy would contain unseen histories inaccessible to our telescopes. Every supermassive black hole would conceal possibilities extending far beyond its own event horizon. Yet this vast picture introduces another mystery. If black holes truly shape universes on such enormous scales, could they also explain some of the surprising features of the galaxies, stars, and cosmic structures we already observe? Perhaps connections exist that are subtler than anyone first imagined. Perhaps the story of black holes has been quietly influencing the visible universe all along. By this point in our journey, black holes no longer appear as isolated curiosities scattered throughout the cosmos. Instead, they have become threads woven into nearly every chapter of cosmic history. Stars create them, galaxies grow around them, gravity reveals them, quantum theory questions them, and some hypotheses suggest they may even give birth to entirely new universes. Yet one of the most remarkable developments in modern astronomy has been the discovery that these seemingly separate stories are deeply connected. The universe, it seems, rarely solves one problem at a time. A discovery in one corner of astronomy often illuminates another. Black holes provide one of the clearest examples of this hidden unity. Consider a galaxy. At first glance, it appears to be an enormous collection of stars moving together through space. The Milky Way alone contains hundreds of billions of stars spread across a disk more than 100,000 light-years wide. Its central black hole, by comparison, occupies an almost unimaginably tiny volume. For many years, astronomers assumed the two evolved largely independently. Stars formed from giant clouds of gas. The central black hole quietly consumed whatever happened to drift too close. The relationship seemed almost accidental. Then observations began revealing an unexpected pattern. As astronomers measured the masses of supermassive black holes in many different galaxies, they noticed something surprising. Larger galaxies tended to possess larger central black holes. More remarkably, the relationship was not random. The mass of a galaxy's central bulge appeared closely linked to the mass of its black hole. This became known as the M-sigma relation, one of the most important empirical discoveries in modern galaxy evolution. The implication was extraordinary. How could an object occupying such a tiny fraction of a galaxy somehow know the size of the galaxy surrounding it? Or perhaps more accurately, How could the galaxy know the mass of its black hole? Neither object could evolve entirely without influencing the other. The connection had to be physical. Astronomers gradually realized that galaxies and black holes grow together when large amounts of gas fall toward the center of a young galaxy. Part of that gas forms new stars. Another portion feeds the central black hole. As the black hole grows, it releases enormous amounts of energy through radiation and powerful jets. That energy pushes against surrounding gas. Sometimes it heats the gas enough to prevent further star formation. Sometimes it drives vast winds capable of carrying material completely out of the galaxy. The result is a remarkable form of cosmic feedback. Stars help feed black holes. Black holes regulate future generations of stars. Neither dominates the relationship. Instead, they participate in an intricate balance that unfolds over billions of years. This realization transformed the way astronomers think about galaxies. A galaxy is no longer viewed simply as a collection of stars orbiting together. It is an evolving ecosystem. Gravity gathers matter. Stars create heavy elements. Supernovae enrich interstellar gas. Black holes regulate the flow of that gas. Dark matter provides the invisible gravitational framework holding everything together. Each component depends upon the others. Remove one piece, and the history changes. This interconnectedness extends even farther. The heavy elements forged inside stars eventually become planets. On at least one planet, chemistry became biology. Biology eventually produced beings capable of asking questions about black holes. In this sense, black holes are connected, however indirectly, to the very existence of observers, without generations of massive stars collapsing into neutron stars and black holes. Many of the elements essential for rocky planets and complex chemistry would never have existed, although black holes themselves do not manufacture those elements. The massive stars that eventually become black holes certainly do. The life and death of stars remain inseparable from the emergence of complexity throughout the cosmos. Modern cosmology increasingly resembles a story of cycles rather than isolated events. Gas becomes stars. Stars become heavier elements. Some stars become black holes. Black holes influence galaxies. Galaxies create new generations of stars. The cycle repeats. If the hypothesis of universe creation were eventually shown to be correct, another cycle might exist above all the others, universes giving rise to universes. It is important to emphasize that this final step remains entirely hypothetical. The earlier cycles are supported by overwhelming observational evidence. The last one awaits confirmation, yet the possibility illustrates an elegant pattern that many physicists find intellectually compelling. Nature often builds complexity through repeated processes operating across vastly different scales. There is another unexpected connection: entropy. Entropy is frequently described as a measure of disorder. Although physicists often think of it more precisely as the number of microscopic arrangements corresponding to a particular large-scale state, one of the great discoveries of 20th century physics was that black holes possess entropy. This insight emerged through the work of Jacob Bekenstein and Stephen Hawking. At first, the idea seemed almost absurd. How could an object from which nothing escapes possess thermodynamic properties? Yet the mathematics proved remarkably persuasive. The entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This relationship has profound implications. Ordinarily, one expects the amount of information contained within an object to grow with its volume. A larger room holds more books than a smaller one. A larger hard drive stores more data than a smaller one. Black holes appear different. Their information content scales with surface area. This observation inspired one of the most influential concepts in modern theoretical physics: the holographic principle. The name comes from ordinary holograms. A flat holographic film can encode the appearance of a three-dimensional image. Similarly, some physicists have proposed that the information describing a region of space may ultimately be encoded on its boundary. This idea emerged most clearly through developments in string theory and quantum gravity. Although still an active area of research, it has become one of the leading conceptual tools for exploring black holes. Its relevance to our documentary is subtle but profound. If space-time itself can encode information in ways fundamentally different from ordinary intuition, then the event horizon may not simply be a one-way boundary. It may participate actively in preserving information that classical physics seemed to lose. Whether this ultimately resolves the information paradox remains uncertain, but it demonstrates once again how seemingly unrelated ideas become deeply intertwined. Thermodynamics, quantum mechanics, General relativity, information theory, cosmology, all converge upon black holes. The deeper scientists investigate these objects, the more connections they uncover. This convergence is not unique in the history of science. Newton united celestial and terrestrial motion. Maxwell united electricity and magnetism. Einstein united space and time. Perhaps the ongoing effort to understand black holes represents another such moment. Not because black holes are more important than every other object in the universe, but because they occupy the rare intersection where nearly every fundamental branch of physics meets. Gravity becomes extreme. Quantum effects become unavoidable. Information becomes mysterious. Thermodynamics acquires geometric meaning. Cosmology begins to overlap with astrophysics. It is as though many independent rivers of scientific thought gradually flow together into a single deep valley. Whether that valley ultimately leads toward universe creation, quantum gravity, or an entirely different destination remains unknown. But the remarkable web of connections already discovered teaches an important lesson. Black holes are no longer merely astronomical objects. They have become laboratories for some of the deepest questions humanity has ever asked. And as new observatories continue exploring the universe with increasing precision, astronomers hope those laboratories may finally begin revealing clues that have remained hidden for generations. The next chapter of this story is already unfolding, carried not only by theory, but by an extraordinary new generation of instruments capable of observing the cosmos in ways that would have seemed impossible only a few decades ago, for most of human history. The night sky appeared almost unchanging. The same constellations returned with each passing season. The planets wandered slowly among the stars. A bright comet might occasionally appear, only to vanish again into the darkness. The heavens seemed distant, serene, and largely beyond reach. Today, the situation is entirely different. Modern astronomy no longer depends upon visible light alone. The universe now speaks through radio waves, infrared radiation, ultraviolet light, X-rays, gamma rays, neutrinos, gravitational waves, and exquisitely detailed computer simulations. Each provides a different window into cosmic reality. Together, they're allowing astronomers to investigate black holes with a level of precision that previous generations could scarcely have imagined. Although none of these tools can see beyond an event horizon, each brings us a little closer to understanding where our current theories succeed, where they begin to fail, and where entirely new physics may eventually emerge. One of the most remarkable instruments ever built is the James Webb Space Telescope. Unlike the Hubble Space Telescope, which primarily observes visible and ultraviolet light, Webb specializes in infrared wavelengths. Infrared light is especially valuable because it can penetrate clouds of dust that would otherwise conceal distant objects. It also allows astronomers to study some of the earliest galaxies ever formed. These observations have produced an unexpected surprise. Several galaxies seen less than 1 billion years after the Big Bang already appear surprisingly mature. Some contain enormous populations of stars. Others seem to host black holes whose masses challenge existing models of cosmic growth. This does not mean standard cosmology has been overturned. Far from it. Astronomers continue to investigate whether these early galaxies formed unusually rapidly, whether their masses have been overestimated, or whether existing models simply require refinement. Scientific progress often begins with careful questions rather than dramatic conclusions. Still, Webb's observations remind researchers that the young universe may have been more efficient at building massive structures than previously thought. That possibility directly affects our understanding of supermassive black holes. If they formed earlier than expected, how did they grow so quickly? The question remains open. Meanwhile, another extraordinary achievement continues from the surface of Earth. The Event Horizon Telescope is unlike any ordinary observatory. Instead of constructing one enormous telescope, astronomers linked radio observatories scattered across the globe, using atomic clocks accurate to billionths of a second. They synchronized observations from continents separated by thousands of kilometers. After combining vast quantities of recorded data, they effectively created a virtual telescope nearly the size of Earth itself. This immense resolving power made it possible to produce the now famous images of black hole shadows. It is worth remembering exactly what these images represent. They do not show the event horizon directly, nor do they reveal the singularity or the interior. Instead, they capture glowing plasma orbiting just outside the black hole. Against this bright background appears a dark central shadow, produced because gravity bends and traps light in the region surrounding the event horizon. The remarkable agreement between these observations and Einstein's predictions has strengthened confidence in general relativity under extremely strong gravitational conditions. Yet astronomers are not satisfied with static pictures alone. Future observations aim to create time-lapse movies showing hot gas swirling around black holes. Such measurements may reveal subtle details of magnetic fields, turbulence, and plasma dynamics that remain poorly understood. Every improvement sharpens our ability to test gravity itself. Another revolution is taking place beneath the Earth rather than above it. Gravitational wave astronomy is still in its infancy. The first direct detection occurred only in 2015. Already, dozens of mergers involving black holes and neutron stars have been observed. Each signal carries a unique fingerprint, the masses of the merging objects, their spins, their orbital motion, the final vibration of the newly formed black hole. Physicists carefully compare every observed waveform with predictions from numerical relativity. Thus far, Einstein's theory continues to perform remarkably well, yet future detectors promise something even more exciting. The planned Laser Interferometer Space Antenna, known as LISA, will operate in space rather than on Earth. 3 spacecraft separated by millions of kilometers will exchange laser beams while orbiting the Sun. Freed from Earth's seismic noise, LISA will become sensitive to gravitational waves with much lower frequencies. These include signals from merging supermassive black holes, systems far larger than those currently detected. Instead of observing only the final moments before collision, LISA may follow some inspiraling systems for months or even years. Such prolonged observations could reveal tiny deviations from theoretical predictions. Even a slight discrepancy might hint at new gravitational physics. Perhaps quantum effects subtly modify the final stages of collapse. Perhaps space-time behaves differently under the most extreme conditions. Or perhaps Einstein's theory will once again prove astonishingly accurate. Either outcome would deepen our understanding. Computer simulations are advancing just as rapidly. Modern supercomputers now model entire galaxies, tracing billions of years of evolution. They follow gas cooling inside dark matter halos. They simulate star formation, supernova explosions, magnetic fields, and the growth of supermassive black holes. These calculations help astronomers compare competing models with observations. If a particular simulation consistently reproduces the real universe more accurately than others, confidence in its underlying assumptions increases. Increasingly, artificial intelligence is assisting this effort. Machine learning algorithms analyze enormous astronomical surveys containing millions of galaxies. They identify patterns too subtle for human observers to recognize easily. They classify black hole candidates. They search for rare gravitational lensing events. They even help reconstruct incomplete observational data. Importantly, artificial intelligence does not replace scientific reasoning. Instead, it serves as a powerful tool for exploring datasets whose sheer size exceeds what traditional methods can comfortably handle. At the same time, particle physicists continue probing conditions resembling those of the early universe. The Large Hadron Collider cannot produce black holes of astrophysical size. Its collisions occur on scales far too small for that. Nevertheless, experiments investigating fundamental particles, quantum fields, and high-energy interactions provide valuable clues about the physics that may eventually contribute to a successful theory of quantum gravity. Every branch of modern physics contributes a different piece to the puzzle. Astronomy observes the largest structures. Particle physics investigates the smallest. Gravitational wave observatories study space-time itself. Computer simulations connect theory with observation. Progress emerges from their combination. And yet, despite this remarkable technological age, the central mystery remains intact. No telescope has seen beyond an event horizon. No detector has measured the geometry deep within a black hole. No experiment has confirmed whether singularities truly exist, or whether quantum gravity replaces them with something entirely different. The possibility that black holes create universes therefore remains exactly where responsible science places it. Not among established facts, not among discarded ideas, but within the growing landscape of serious hypotheses awaiting stronger evidence. Perhaps the coming decades will provide that evidence. Perhaps entirely new observatories will reveal subtle signatures no one has yet anticipated. Or perhaps the greatest breakthrough will arrive not through a telescope at all, but through a deeper mathematical understanding of gravity and quantum mechanics. History suggests that nature often reveals her deepest secrets only after decades of patient observation. Every generation builds instruments capable of asking questions that the previous generation could not, and every answer, almost inevitably, reveals an even deeper mystery waiting beyond it. The extraordinary tools now exploring the cosmos have brought humanity closer than ever before to the hidden heart of black holes. Yet they have also reminded us of something equally profound. The closer we approach the frontier of knowledge, the more carefully we must distinguish between what we have discovered and what we still do not know. There is a quiet temptation that accompanies every great scientific mystery. When evidence grows scarce, certainty often grows louder. History shows this pattern again and again. Wherever observation reaches its limits, confident explanations tend to multiply. Ancient maps filled unexplored oceans with elaborate coastlines that did not exist. Early astronomers imagined perfect celestial spheres because they seemed mathematically beautiful. Even in modern times, elegant theories sometimes survive for decades before nature quietly reveals their flaws. Black holes invite the same temptation. Their interiors are forever hidden behind the event horizon. Their deepest conditions cannot be recreated in any laboratory. The mathematics becomes increasingly uncertain precisely where direct observation becomes impossible. If ever there were a place where humility belongs, it is here. One of the most important habits in science is learning to distinguish between different kinds of ignorance. Sometimes scientists do not know the answer because they have not yet collected enough data. Sometimes they lack the necessary technology. Sometimes the mathematics has not yet matured. And occasionally, nature itself places limits upon what can ever be observed directly. Black holes may involve all four. The first limitation is observational. Every telescope depends upon information arriving from distant objects. Whether that information takes the form of light, gravitational waves, neutrinos, or particles, something must escape the source before it can be measured. The event horizon prevents exactly that. Whatever happens beyond it cannot communicate directly with the outside universe. No improvement in optical technology changes this fact. A larger mirror cannot collect photons that never arrive. A more sensitive detector cannot measure signals that never escape. This is not merely a technological challenge. It is built into the geometry of space-time itself. The second limitation is theoretical. General relativity has passed every observational test so far under astrophysical conditions. Quantum mechanics has proven equally successful in the microscopic world. Yet the two theories remain fundamentally incompatible in the environments where both become equally important. Physicists know with great confidence that a more complete framework must exist. They simply do not yet know what form it takes. This situation is unusual. Normally, new theories arise because old ones fail experimentally. Here, the conflict appears first within mathematics itself. General relativity predicts singularities. Quantum mechanics resist the destruction of information. Each theory seems to challenge the other long before observations can decide between them. The third limitation concerns scale, the Planck length. Where many researchers expect quantum gravity to become important, is unimaginably small. The corresponding energies are unimaginably large. Even humanity's most powerful particle accelerators remain enormously distant from these conditions. To probe Planck-scale physics directly would require energies many trillions of times greater than anything presently achievable. Nature kindly provides such conditions only in extraordinary places, the earliest moments of the universe, the interiors of black holes, possibly the collisions of particles at energies far beyond current technology. Unfortunately, two of those environments remain inaccessible. The fourth limitation is perhaps the most subtle. It concerns interpretation. Even when observations become available, they rarely speak for themselves. Astronomers must decide which theoretical framework best explains the data. Sometimes several different explanations fit equally well. This is exactly where black hole research stands today. Suppose future gravitational wave observatories detect a tiny deviation from Einstein's predictions during a black hole merger. What would it mean? Would it confirm quantum gravity? Would it support loop quantum gravity rather than string theory? Would it indicate some entirely different phenomenon not yet imagined? One observation rarely answers every question. Instead, it gradually eliminates possibilities. Scientific understanding grows through accumulation rather than revelation. This patient process explains why physicists remain cautious when discussing universe creation inside black holes. The idea is intellectually compelling. It resolves certain mathematical difficulties in some theoretical models. It connects naturally with broader questions about cosmology. Yet compelling ideas are not automatically correct. Nature has repeatedly shown that intuitive explanations can fail. Even elegant mathematics must eventually confront observation. There is another reason for caution. Many different approaches to quantum gravity predict that singularities disappear, but they do not all predict new universes. Some suggest quantum cores. Some propose stable remnants. Others envision subtle modifications to space-time that preserve information without requiring cosmological offspring. Removing the singularity does not automatically produce a new cosmos. Several additional assumptions are required. Recognizing this distinction prevents speculation from quietly becoming accepted fact. This careful separation between knowledge and possibility is one of science's greatest strengths. It allows imagination to remain extraordinarily bold while demanding equally rigorous standards of evidence. Perhaps nowhere is this balance more visible than in discussions surrounding the Big Bang. Popular language often speaks as though cosmologists know exactly what happened at the beginning of time. The reality is more nuanced. Astronomers possess overwhelming evidence that the universe expanded from an earlier hot, dense state. The cosmic microwave background confirms it. The abundance of light elements confirms it. The expansion of galaxies confirms it. These observations form one of the strongest scientific frameworks ever assembled. What remains uncertain is what happened at the earliest fraction of a second. Inflation may explain many observed features. Quantum gravity may describe even earlier conditions. Perhaps the Big Bang marked an absolute beginning. Perhaps it did not. Current evidence cannot yet decide. The same careful language applies to black holes. Astronomers know that event horizons exist. They know matter crosses them. They know black holes merge. They know Hawking radiation is strongly supported theoretically. Although it has not yet been detected directly from astrophysical black holes, because the predicted signal is extraordinarily weak. Beyond these foundations lies increasing uncertainty. The singularity, information preservation, quantum gravity, universe creation. Each step moves farther from direct evidence. This does not make such ideas unscientific. It simply places them in different categories of confidence. Recognizing these categories protects science from two opposite mistakes. The first is excessive skepticism. Rejecting every new idea simply because it has not yet been proven would halt scientific progress entirely. The second is excessive certainty. Accepting fascinating hypotheses as established reality would be equally damaging. Progress requires navigating carefully between these extremes. History suggests that this balance is often rewarded. Few physicists expected gravitational waves to be measured within a century of Einstein's prediction. Few imagined that black hole shadows would ever be photographed. Yet both achievements eventually became reality through patient technological development. Perhaps today's speculative ideas will follow a similar path, or perhaps entirely different explanations, not yet conceived, will ultimately prove correct. That possibility may be the most exciting of all. The universe has repeatedly demonstrated that its true workings are richer than humanity's first attempts to describe them. Every generation inherits mysteries. Every generation solves some while discovering others. Our own generation stands at one of those rare frontiers. We understand enough to recognize the questions. We do not yet understand enough to answer them. And somewhere beyond every event horizon, beyond every equation approaching its limit, beyond every observation that modern instruments can collect, the next great chapter of physics may already exist, waiting for the moment when evidence and understanding finally meet. There is a place in every scientific discipline where knowledge becomes exploration, maps fade into sketches, measurements give way to estimates. Established theories begin to overlap with possibilities that have not yet been tested. For astronomy, black holes have become one of those places, not because scientists have reached the end of discovery, but because they have arrived at the edge of what their current tools and theories can confidently describe. This frontier has a name: quantum gravity. It is one of the greatest unfinished projects in all of modern physics. Its goal is deceptively simple: to unite the two most successful scientific theories ever created into a single. Deeper understanding of reality. General relativity describes gravity. Quantum mechanics describes everything else at the smallest scales. Separately, both have achieved astonishing success. Together, they remain incomplete. The difficulty is not merely mathematical. It is conceptual. General relativity treats space-time as a smooth, continuous geometry. Mass and energy curve this geometry, producing what we experience as gravity. The theory is elegant because space and time themselves become dynamic participants in the universe. Quantum mechanics paints a very different picture. At microscopic scales, certainty dissolves into probability. Particles do not possess perfectly defined positions and velocities simultaneously. Fields fluctuate constantly. Even what we call empty space contains restless quantum activity. The vacuum is not truly empty. It is alive with temporary fluctuations that appear and disappear according to the rules of quantum theory. Both descriptions are extraordinarily accurate within their respective domains. Yet when gravity becomes extremely strong and distances become extraordinarily small, the assumptions underlying each theory begin to conflict. This is precisely the environment expected near the center of a black hole. It may also describe the earliest measurable moments of the universe itself. That coincidence is one reason black holes attract such intense interest. They are not merely unusual astronomical objects. They are natural laboratories where the deepest foundations of physics converge. One way to appreciate the challenge is to think about scale. Human experience occupies an extraordinarily narrow range. We live comfortably between the very large and the very small. A mountain seems enormous. An atom seems unimaginably tiny. Yet compared with the true scales explored by modern physics, both lie surprisingly close together. Galaxies exceed mountains by an incomprehensible margin. The Planck length lies beyond atoms by an equally astonishing distance, somewhere near that Planck scale. Many physicists suspect the smooth fabric of space-time gives way to something more fundamental. But what? That question has inspired several ambitious research programs. Loop quantum gravity proposes that space-time itself possesses a discrete structure, instead of a perfectly continuous fabric. Space may consist of tiny quantum units connected into intricate networks. Distance, area, and volume would become quantized, somewhat as energy already is in quantum mechanics. If this picture proves correct, singularities may disappear because space-time cannot be compressed indefinitely. There would be a smallest meaningful scale. Compression would eventually encounter the fundamental architecture of space itself. String theory approaches the problem differently. Instead of changing space-time first, it changes the nature of matter. Elementary particles become tiny vibrating strings whose oscillations determine their observable properties. One remarkable feature of string theory is that gravity emerges naturally within its mathematics, rather than being added separately. It appears as one consequence of the underlying framework. The theory also predicts additional spatial dimensions beyond the familiar three. These dimensions would be extraordinarily small or otherwise hidden from everyday observation. Whether nature truly contains them remains unknown. Both approaches represent decades of careful mathematical work. Neither has yet received decisive experimental confirmation. This situation sometimes frustrates those outside physics. Why spend so much effort developing theories that cannot yet be tested directly? History offers a reassuring answer. Scientific progress often unfolds in stages. James Clerk Maxwell predicted radio waves decades before technology could generate or detect them. Einstein described gravitational waves a century before humanity measured one. Paul Dirac's equations implied the existence of antimatter before any antiparticle had been observed. Mathematics occasionally reaches beyond experiment. When it does so successfully, later generations build the instruments needed to test its predictions. Quantum gravity may simply require similar patience. Meanwhile, researchers continue searching for indirect clues. Perhaps tiny modifications to gravitational waves will reveal quantum corrections. Perhaps the early universe preserved subtle signatures from Planck-scale physics. Perhaps black hole evaporation, if ever observed in sufficient detail, will expose departures from classical expectations. Even the smallest anomaly could point toward a deeper framework. Some physicists have suggested that space-time itself may not be fundamental at all. This idea represents one of the most radical shifts currently under consideration. Ordinarily, space seems like the stage upon which everything else exists. Matter moves through it. Light travels across it. Time measures change within it. But several modern approaches hint that space-time may instead emerge from something even deeper. Quantum entanglement has become central to this discussion. Entanglement describes situations in which particles share quantum relationships that cannot be explained independently. Measurements performed on one immediately constrain the possible outcomes for the other. Even across enormous distances, these correlations do not transmit usable information faster than light. but they reveal a profound interconnectedness absent from classical physics. Over the past 2 decades, theoretical work has uncovered surprising relationships between entanglement and the geometry of space-time itself. Some researchers now explore whether the fabric of the universe may actually emerge from patterns of quantum information. If that remarkable possibility proves correct, then gravity, space-time, and perhaps even black hole interiors may arise from principles more fundamental than geometry alone. The implications are profound. The event horizon would no longer represent merely a boundary in space. It might reflect deeper rules governing information itself. Once again, we must distinguish possibility from established knowledge. The mathematics supporting these ideas is sophisticated. The observational evidence remains incomplete. No experiment has yet demonstrated that space-time emerges from quantum entanglement. Yet the convergence of multiple theoretical approaches has encouraged serious investigation. Increasingly, physicists recognize that black holes force questions extending beyond astronomy. What is space? What is time? What is information? What is reality constructed from at its deepest level? These questions once belonged largely to philosophy. Today they occupy the frontiers of theoretical physics. Remarkably, every path toward answering them seems eventually to pass through black holes. Not because black holes are magical, not because they violate known science, but because they naturally combine the strongest gravity with the smallest relevant scales. Exactly where our current theories overlap. In this sense, black holes function like mountain passes. Many separate scientific trails climb toward them from different directions. General relativity approaches from one side, quantum mechanics from another, thermodynamics from a third, information theory from a fourth. Near the summit, the paths begin to converge. The landscape becomes unfamiliar. The air grows thinner. The destination is visible only in fragments. No one yet knows what lies beyond the final ridge. Perhaps a successful theory of quantum gravity will reveal that black holes truly can generate new universes. Perhaps it will explain the information paradox without requiring such an outcome. Perhaps it will uncover an entirely different picture that none of today's leading ideas has anticipated. History encourages caution. Nature has repeatedly surprised even her most brilliant interpreters. Yet history also encourages optimism. Every previous frontier eventually yielded to patient observation, deeper mathematics, and new ways of asking old questions. The frontier surrounding black holes is unlikely to be different. Somewhere beyond our present understanding, a more complete description of reality almost certainly waits. When it finally emerges, it may not simply explain black holes. It may reshape our understanding of the universe itself, revealing that the greatest mystery was never what happens inside a black hole, but what the existence of black holes has been trying to teach us about reality all along. Throughout history, humanity has repeatedly discovered that reality is larger than the stories first told about it. The Earth was once thought to be the fixed center of creation. Then it became one planet among many. The Sun, once regarded as extraordinary, became one ordinary star within a galaxy of hundreds of billions. The Milky Way itself, long believed to encompass everything that existed, became one galaxy among hundreds of billions more. Each discovery required more than new observations. It required a new way of thinking. Perhaps the deepest consequence of black hole research is not what it may reveal about black holes themselves. It is how it may transform our understanding of reality. Science often progresses by replacing familiar concepts with deeper ones. Time once seemed universal. Einstein revealed that every observer experiences it differently. Empty space once appeared truly empty. Quantum physics show that even the vacuum possesses restless activity. Matter once seemed solid and continuous. Modern particle physics uncovered an invisible world of quantum fields whose excitations give rise to everything we see. Each revolution expanded rather than diminished reality. Black holes may represent another such expansion. If the most successful theories of physics both reach their limits inside these objects, then perhaps the assumptions shared by those theories also require reconsideration. One of those assumptions concerns beginnings. Human beings naturally think in terms of first events. Every story begins somewhere. Every journey starts with a first step. Every building has a foundation. This habit serves us well in everyday life. Yet cosmology repeatedly challenges ordinary intuition. The Big Bang is often described as the beginning of the universe. That statement is accurate within the framework of the standard cosmological model. Time, as presently understood, can be traced backward only to extremely early moments before our theories become incomplete. What happened before remains uncertain. Some physicists therefore hesitate to use the word before at all. If time itself emerged during the earlier stages of cosmic evolution, then asking what happened before time may resemble asking what lies north of the North Pole. The question assumes a framework that may no longer apply. Now consider the possibility of black hole cosmology. If universes emerge from collapsing regions inside older universes, then beginnings become more subtle. The birth of one universe may also represent the continuation of another process occurring elsewhere. Neither picture eliminates mystery, it merely relocates it. Instead of asking why our universe began, we might ask why the larger process exists. Questions evolve, they rarely disappear. Another deeply rooted assumption concerns scale. Ordinarily, larger objects contain smaller ones. A city contains buildings. Buildings contain rooms. Rooms contain people. Black hole cosmology invites a more unfamiliar possibility. A region appearing microscopically small from one perspective might contain an entire expanding universe from another. This does not violate ordinary geometry because the relationship is not one of simple physical size. It is a consequence of space-time itself. General relativity has already taught us that distances depend upon geometry rather than intuition. The shortest path between 2 points in curved space-time need not resemble the straight lines of ordinary experience. If space-time possesses structures richer than everyday geometry suggests, then familiar ideas of inside and outside may become surprisingly inadequate. The consequences extend even further. Consider causality. Throughout daily life, causes precede effects. A seed grows into a tree, a star forms before it shines. Planets condense after their parent star begins to form. The order seems obvious, yet relativity revealed that different observers may disagree about the timing of distant events. Quantum mechanics introduced correlations that defy classical expectations, while preserving causality in subtle ways. Neither theory destroys cause and effect. Instead, both reveal that causality operates within a framework more sophisticated than common experience suggests. If universes arise from black holes, causality may acquire another layer. Events inside a daughter universe unfold according to their own internal timeline. Observers there construct histories entirely consistent within their own space-time. The processes leading to their cosmic birth belong to a larger structure inaccessible from within. This is not unlike our own situation. Everything astronomers observe occurs inside the universe. Any process responsible for the existence of the universe itself, if such a process exists, lies outside ordinary observational history. Again, the similarity should not be mistaken for proof. It merely illustrates how black hole cosmology reshapes familiar questions. Perhaps the most profound implication concerns information. Modern physics increasingly suggests that information is not merely a useful bookkeeping device. It may be one of the fundamental ingredients of reality itself. The information paradox surrounding black holes has already encouraged new ideas linking gravity, thermodynamics, quantum mechanics, and geometry. If future discoveries confirm that space-time emerges from deeper informational principles, then black holes may become essential to understanding how reality organizes itself. In that picture, matter, energy, space, and time would no longer occupy separate categories. They would become different expressions of more fundamental relationships. This possibility remains speculative, yet its influence upon theoretical physics has been immense. Many of today's most active research programs investigate information as carefully as they investigate particles. The shift is subtle but significant. Physics is no longer asking only what the universe is made of. Increasingly, it also asks how reality stores, transforms, and preserves information. Black holes stand at the center of that inquiry. Another consequence touches our place within the cosmos. For centuries, scientific discoveries have steadily removed humanity from privileged positions. We are not located at the center of the solar system, nor at the center of the galaxy, nor at the center of the observable universe. Black hole cosmology continues this trend. If correct, our universe would not necessarily occupy a unique position either. It could represent one chapter within a much larger cosmic genealogy. Such an idea might initially appear to diminish significance. History suggests the opposite. Every expansion of the cosmic perspective has enriched rather than impoverished humanity's understanding. Learning that Earth circles the Sun did not make our planet less remarkable. Discovering billions of galaxies did not make the night sky less beautiful. Instead, Each revelation deepened our appreciation of reality. Perhaps the same would occur here. A universe connected to others through processes extending beyond present observation would not become less meaningful. It would become part of a story vastly older and larger than previously imagined. Still, careful science requires restraint. No observation has demonstrated that universes reproduce through black holes. No telescope has detected a daughter cosmos. No experiment has verified such a genealogy. The hypothesis remains exactly that. Hypothesis. Its importance lies not in certainty, but in the questions it encourages physicists to ask. Questions often shape science more profoundly than answers. The right question can guide decades of observation, inspire entirely new mathematical frameworks, and lead to discoveries no one initially anticipated. Whether black holes ultimately create universes may prove less important than the search itself. That search has already transformed our understanding of gravity, information, thermodynamics, and space-time. It continues to inspire new generations of astronomers and physicists exploring one of nature's deepest frontiers. And if the answers eventually reveal that black holes are not cosmic beginnings after all, they will almost certainly reveal something equally unexpected. For the history of science contains one lesson repeated with remarkable consistency. Reality is almost always more subtle, more interconnected, and more beautiful than humanity first expects. The next step in our journey is therefore not to look backward toward the ancient past, but forward across immense stretches of cosmic time. For if black holes participate in the creation of universes, what role might they play in the far future of reality itself when astronomers look into the night sky? They are also looking backward through time. The light reaching Earth from the Moon is a little more than 1 second old. Light from the Sun left its surface about 8 minutes ago. The glow from the Andromeda Galaxy began its journey roughly 2.5 million years before the first humans appeared. The most distant galaxies visible to modern telescopes allow us to glimpse the universe as it existed more than 13 billion years ago. Astronomy has become an exploration of history, yet the same physical laws that allow us to reconstruct the distant past also permit us to explore the distant future. Not with certainty, not in every detail, but with carefully reasoned projections grounded in observation and well-tested theory. If black holes truly have a role in creating universes, then their greatest influence may not lie in the ancient past at all. It may unfold across spans of time almost impossible to comprehend. To appreciate this possibility, we must first consider the future of our own universe according to standard cosmology. At present, observations indicate that cosmic expansion is accelerating. Galaxies are not merely moving apart because of their initial motion after the Big Bang. The expansion itself appears to be speeding up. The cause is commonly attributed to dark energy, a phenomenon whose nature remains one of the greatest unsolved problems in physics. Whatever dark energy ultimately proves to be, its effects are measurable. Over billions of years, distant galaxies will continue drifting farther away. The night sky seen by civilizations in the unimaginably distant future will look very different from ours. Galaxies beyond our local group will gradually disappear beyond the cosmic horizon. Their light will become so stretched by expansion that it can no longer reach future observers. Eventually, only the merged descendants of the Milky Way and Andromeda, together with a handful of nearby galaxies, may remain visible. The wider universe will fade from view, yet inside those surviving galaxies, stellar evolution will continue. New stars will form from remaining clouds of gas. Others will quietly exhaust their nuclear fuel. White dwarfs, neutron stars, black holes. The familiar cycle will persist, although ever more slowly as raw material becomes scarce. After trillions of years, star formation is expected to decline dramatically. Most galaxies will consist largely of long-lived stellar remnants orbiting through an increasingly dark cosmos. This stage is sometimes called the degenerate era. The name reflects the dominance of degenerate matter inside white dwarfs and neutron stars rather than any deterioration of physical law. Even then, black holes remain. In fact, they become increasingly important. Without bright young stars dominating the universe, black holes emerge as some of the last major engines of gravitational evolution. Occasionally, stellar remnants collide. Sometimes a neutron star wanders too close to a black hole. Over immense periods, gravitational interactions gradually reshape entire galaxies. Black holes continue merging. Each merger creates a larger black hole. Each gravitational encounter redistributes energy among surrounding objects. Timescales that seem unimaginably long by human standards become ordinary within cosmic history. Then another remarkable process enters the picture. Hawking radiation. According to Stephen Hawking's calculations, black holes slowly lose energy through quantum effects associated with the event horizon. The larger the black hole, the slower this process occurs. A stellar mass black hole would survive for an almost inconceivably long period. A supermassive black hole containing billions of solar masses would persist vastly longer still. The numbers become almost meaningless in everyday language. Some of the largest black holes may require around 10,100 years or more to evaporate almost completely. For comparison, the current age of the universe is about 1.38 10 years. The difference between these numbers is so enormous that ordinary intuition simply cannot grasp it. Black holes therefore become some of the longest-lived structures predicted by known physics. If the standard picture is correct, they eventually evaporate. If some form of quantum gravity significantly alters Hawking's conclusions, their ultimate fate could differ. Researchers continue exploring these possibilities. Now let us carefully return to our central hypothesis. Suppose black holes do create daughter universes. What would that imply for the far future? Interestingly, it would suggest that while our universe gradually grows colder, darker, and more diffuse, entirely new universes may continue beginning elsewhere. To observers living inside those new universes, none of this ancient history would be visible. Their own cosmic clocks would start near their own hot, dense beginning. Stars would form, galaxies would evolve, planets might appear. Perhaps observers would eventually ask questions remarkably similar to our own. They too might wonder where their universe came from. They too might discover black holes. They too might eventually ask whether those black holes created still other universes. The pattern becomes almost recursive, not because evidence demands it, but because the hypothesis naturally extends itself across generations of cosmic evolution. One universe produces black holes. Some black holes produce new universes. Those universes produce stars. Stars produce black holes. The cycle repeats. This idea inspired Lee Smolin's proposal of cosmological natural selection, which we encountered earlier. In his framework, universes capable of producing abundant black holes become statistically more common over many generations. The proposal remains speculative. No observational evidence has confirmed that such cosmic inheritance occurs. Nevertheless, it illustrates how the far future of cosmology could resemble an ongoing evolutionary process rather than a single isolated event. There is another possibility that deserves equal attention. Perhaps black holes do not create universes at all. Perhaps quantum gravity resolves singularities in some entirely different way. Even then, black holes remain central to the future of the cosmos. Their mergers, evaporation, and gravitational influence continue shaping cosmic history for periods of time vastly exceeding the current age of the universe. Either way, black holes become among the final great actors upon the cosmic stage. One intriguing consequence of these enormous timescales concerns perspective. Human civilization has existed for only a tiny fraction of Earth's history. Earth itself formed long after the Milky Way was already mature. Our galaxy is only one among hundreds of billions. Against the backdrop of black hole evolution, even galaxies begin to seem temporary. The universe unfolds patiently. Processes lasting trillions upon trillions of years become ordinary chapters within its larger narrative. This realization carries a certain quiet beauty. The cosmos is under no obligation to move at human speed. Stars evolve over millions of years. Galaxies over billions. Black holes over durations that challenge language itself. Reality unfolds according to its own rhythm. Whether black holes eventually become seeds for new universes or simply the final remnants of dying galaxies, they remind us that cosmic history extends far beyond the horizons of human experience, and yet, despite all these projections into the unimaginably distant future, one final question remains. When we began this journey, black holes seemed like endings. Now they appear far more mysterious. Perhaps they are endings. Perhaps they are beginnings. Perhaps they are both. As we prepare to return to the question with which we began, we can see that the greatest transformation has not occurred in the black holes themselves. It has occurred in the way we have learned to think about them. At the beginning of this journey, a black hole seemed almost simple. It was the graveyard of stars, a place where gravity became so powerful that nothing could escape. An object defined primarily by absence. No light, no return, no future beyond the event horizon. That picture was not wrong. It was simply incomplete. Much as the ancient picture of the solar system was not entirely false, the sun really does rise each morning. The stars really do appear to circle the heavens each night. Those observations remain perfectly valid within ordinary experience. What changed was not the sky itself, it was the framework through which humanity understood it. Something similar has happened throughout our exploration of black holes. We began with an object that appeared to represent an ending. Then astronomy gradually revealed another layer. Black holes are not rare accidents. They are fundamental components of galaxies. They influence the birth of stars, the evolution of galaxies, and the distribution of matter across the observable universe. Far from being passive holes in space, they participate continuously in cosmic history. Another layer followed. General relativity describes their exterior with extraordinary precision. The paths of stars, the bending of light, the rhythm of gravitational waves, the silhouettes recorded by the Event Horizon Telescope. Every one of these observations strengthens our confidence in Einstein's remarkable theory. Yet confidence gave way to uncertainty precisely where gravity became strongest. The singularity. There. The equations that describe so much of the universe with astonishing success begin to signal their own incompleteness. Rather than providing final answers, they invite deeper questions. That realization changed the nature of the mystery. The question was no longer whether black holes exist. That had already been answered. The question became whether the deepest interior truly resembles the mathematical singularity predicted by classical relativity, or whether quantum gravity replaces it with something richer. As we followed that path, another transformation occurred. The discussion shifted from observation to possibility. Not every possibility carries equal weight. Some rest upon established evidence. Others emerge from carefully developed mathematical frameworks. Still others remain speculative attempts to explore where current knowledge may eventually lead. Throughout this journey, it has been important to keep these categories distinct. Science does not become stronger by pretending certainty where none exists. It becomes stronger by acknowledging uncertainty honestly. That honesty is one of its quiet strengths. Among the many ideas explored by physicists, one stood apart because of its extraordinary implications. If singularities never actually form, if quantum gravity eventually halts collapse, if expanding space-time can emerge within the hidden interior, then every black hole might represent more than an ending. It might also represent a beginning. Again, this remains a hypothesis. No telescope has observed a daughter universe. No experiment has confirmed such a process. Yet the possibility illustrates something deeper than the hypothesis itself. It demonstrates how science often progresses. Researchers ask questions large enough to reshape entire fields. Most proposed answers eventually prove incomplete. A few survive. Occasionally, one changes humanity's understanding forever. History offers many examples. The Earth orbiting the Sun, the existence of galaxies beyond the Milky Way, the expansion of the universe, gravitational waves, black holes themselves. Each began as an idea whose evidence accumulated gradually over many years. Whether universe creation through black holes will someday join that list remains unknown. But the question has already proven valuable. It has inspired new approaches to quantum gravity. It has deepened research into the information paradox. It has encouraged unexpected connections between thermodynamics, geometry, quantum mechanics, and cosmology. Even if the hypothesis ultimately proves incorrect, the search may still reveal entirely different discoveries that no one presently anticipates. That possibility reflects another recurring lesson from astronomy. Nature rarely answers exactly the question we first ask. Instead, she often reveals a richer landscape than the one we originally imagined. Astronomers searching for planetary motions discovered gravity. Researchers studying the spectrum of heated objects uncovered quantum mechanics. Investigations into radio interference accidentally revealed the cosmic microwave background, providing one of the strongest confirmations of the Big Bang. Unexpected discoveries often become the most important ones. Perhaps the same will prove true here. The effort to understand black holes may eventually reveal something more profound than whether they create universes. It may reveal what space-time itself truly is, or why information seems woven so deeply into the laws of physics, or how gravity emerges from quantum reality. Questions that once appeared separate now seem increasingly connected. As the branches of physics converge, the mystery surrounding black holes begins to resemble a crossroads rather than a destination. Every major road appears to pass through them. General relativity, quantum mechanics, thermodynamics, information theory, cosmology. Each arrives carrying its own language. Each departs carrying new questions. Perhaps this convergence is itself a clue. Perhaps black holes are not exceptional because they destroy matter. Perhaps they are exceptional because they expose the limits of every framework humanity currently possesses. Whenever a scientific theory reaches its limit, two possibilities exist. Either the theory survives unchanged, or it becomes part of something larger. Newton survived within Einstein's relativity. Classical physics survived within quantum mechanics. Maybe general relativity and quantum mechanics will someday survive within an even deeper understanding still waiting to be discovered. If that day arrives, black holes may appear very different from how they seem today, not because the observations will change. The event horizons will remain. The gravitational waves will remain. The galaxies will remain. What changes is interpretation. The same observations may eventually fit into a broader picture that humanity cannot yet fully imagine. That realization brings us quietly back to the beginning. When we first looked toward the darkness surrounding a black hole, it seemed natural to think of it as the end of a story. Now that same darkness carries another possibility, not certainty, not proof, but possibility. It reminds us that the greatest mysteries in science are rarely empty spaces waiting to be filled. They are thresholds, places where one understanding gives way to another. Black holes may ultimately prove to be such a threshold. Whether they conceal new universes or something entirely different, they already reveal one unmistakable truth. The universe is richer than the maps we have drawn so far, and somewhere beyond the event horizon, beyond the reach of every telescope and every signal that can ever return, reality continues according to laws that humanity has only just begun to glimpse. The oldest stories humanity ever told about the sky shared a common theme. Beyond the familiar world lay a great unknown. The stars mark the boundary between what could be seen and what could only be imagined. For thousands of years, that boundary remained fixed. Then the telescope arrived. The unknown did not disappear. It simply moved farther away. Each generation has pushed that horizon outward. The planets became worlds. The stars became suns. The Milky Way became one galaxy among hundreds of billions. The observable universe itself expanded into a cosmos stretching nearly 14 billion years into the past. With every discovery, one lesson returned with remarkable consistency. Knowledge does not erase mystery. It refines it. Black holes represent the newest horizon in that long tradition. They are among the most thoroughly studied objects in modern astronomy. Their masses can be measured. Their influence upon nearby stars can be calculated with extraordinary precision. Their mergers ripple across the universe as gravitational waves. Their shadows have even been photographed against glowing clouds of superheated plasma. And yet, at their very center, they still conceal one of the deepest unanswered questions in science. What truly happens beyond the event horizon? During this journey, we have followed that question through observation, mathematics, theory, and speculation. We have seen where evidence is strong, where uncertainty begins, and where imagination must remain disciplined by honesty. The observations are clear. Massive stars collapse into black holes. Supermassive black holes occupy the centers of many galaxies. Gravity behaves exactly as Einstein's theory predicts across an astonishing range of observations. Gravitational waves confirm black hole mergers. The Event Horizon Telescope confirms the existence of event horizons consistent with general relativity. These discoveries belong to established science. The mysteries begin deeper inside. Classical relativity predicts singularities. Quantum mechanics suggests that information should not simply disappear. Reconciling those two ideas has become one of the central goals of modern theoretical physics. No universally accepted solution has yet emerged. Several promising approaches exist: loop quantum gravity, string theory, holographic ideas, quantum information approaches, other developing frameworks. Each contributes valuable insights. None has yet provided the final answer. Among these possibilities lies the idea that first inspired this documentary. Perhaps black holes create universes. It is an idea at once simple and astonishing. If gravitational collapse never reaches an actual singularity, if quantum gravity replaces infinite density with new physical behavior, if expanding spacetime can emerge beyond the point where classical equations fail, then what appears to us as the death of a star might simultaneously become the birth of a new cosmos. Perhaps that single word matters, because science advances not by replacing uncertainty with confidence, but by replacing uncertainty with better evidence. The distinction between possibility and proof has accompanied us throughout this exploration. It deserves to remain with us until the very end. No observation has yet confirmed that black holes generate universes. No experiment has demonstrated such a process. No telescope has looked beyond an event horizon. The hypothesis remains open. Its value lies not only in whether it ultimately proves correct, but in the questions it compels physicists to investigate. Those questions have already transformed entire fields. The information paradox reshaped thinking about quantum gravity. Black hole thermodynamics connected gravity with entropy. Holographic ideas revealed unexpected relationships between geometry and information. Gravitational wave astronomy opened an entirely new way of observing the universe. Every answer uncovered another question waiting beyond it. Perhaps that is the deepest lesson black holes have offered. They remind us that science is not a collection of final truths. It is a continuing conversation with nature. Each observation becomes a question. Each equation becomes an invitation. Each mystery becomes the beginning of another journey. That conversation has been unfolding for centuries. Copernicus asked whether Earth truly stood still. Galileo asked what the telescope might reveal. Newton asked why planets move. Einstein asked what gravity really is. Hawking asked what happens when quantum mechanics meets the event horizon. Today's generation asks whether space-time itself has a deeper foundation than we presently understand. Tomorrow's generation will almost certainly ask questions that none of us have yet imagined. The universe has a remarkable habit of surprising those willing to look carefully. Again and again, reality has proven more subtle than intuition, more interconnected than appearance, more elegant than expectation. The greatest discoveries rarely arrive because scientists seek confirmation of what they already believe. They arrive because nature quietly reveals something unexpected. Perhaps that will happen here as well. Perhaps the black holes scattered throughout the cosmos truly conceal the seeds of new universes. Perhaps they preserve information in ways no current theory fully anticipates. Perhaps they will eventually reveal that space, time, matter, and information emerge from principles still beyond today's mathematics. Or perhaps the true answer will differ from every hypothesis discussed in this documentary. Science has taught us never to underestimate reality's capacity for originality. There is a quiet beauty in that uncertainty. It reminds us that the universe is not a puzzle nearly completed. It is an unfolding landscape whose horizon continually recedes as knowledge advances. Every generation inherits mysteries from those who came before. Every generation leaves new mysteries for those who follow. Black holes stand among the greatest of those inheritances, not because they are the largest objects, not because they are the brightest. Quite the opposite. They are powerful precisely because they hide so much. The darkness surrounding them is not merely an absence of light. It is a reminder of the limits of present understanding. Yet history offers reason for optimism. Every major mystery that humanity has approached with patience, careful observation, honest skepticism, and mathematical imagination has yielded extraordinary discoveries. There is every reason to believe that black holes will eventually do the same. When that day comes, the answer may reshape cosmology. It may redefine gravity. It may alter our understanding of time itself. Or it may reveal that the most extraordinary truth was not hidden inside black holes at all, but in the deeper principles connecting every star, every galaxy, every atom, and every moment of cosmic history into one coherent universe. Until then, the event horizon remains exactly what every great frontier has always been. Not the end of exploration, but the place where exploration truly begins, as the night sky stretches silently above us. Filled with ancient starlight and unseen black holes, it offers one final reminder. The universe does not ask us to fear its mysteries. It invites us to keep wondering, and perhaps somewhere beyond an event horizon that no light can ever cross. The next great chapter of cosmic understanding is already waiting for those willing to ask the next question.